Tu adesso, che adesso fai.
Welcome to this session on the ESA Science Cluster for Hydrology. So my name is Espen Volden. I'm working in the science sections inside the Green Solutions division in ESA in ESRIN, Frascati. So I'll be co-chairing this session together with my colleague Karim Dush.
Good morning, everybody.
So I'll give a little introduction before we start with a number of short project presentations. Let me see, get this started. Yep. So the objectives of this session are to show a bit what projects we have in ESA on the subject of water cycle science and hydrology, and see what are the latest results, but in a very condensed format. See if we can identify some common goals and potential topics for collaboration between projects, because that's kind of a key focus or objective of a science cluster. We should also discuss some ideas for new activities that we have in ESA. Karim will show you something. When we will officially launch the ESA Science Cluster for Hydrology and discuss the next step for the cluster. What happened now? Did I jump in the... Okay. Okay. So just to say what we're doing in our science section in ESRIN, Earth Observation Science, what we're doing is that we are engaging the community in events like what we have today and with the whole Hydrospace workshop. We are developing new methods and observation products that we then try to use in cases where we advance Earth system science. We contribute to scientific campaigns where we can get some additional data that we can use for example, for validation. We are doing training courses. We are developing tools like our virtual labs or open science tools. We are doing networking and partnerships, which the cluster is an example of. And we are trying to put or feed the results from what we have from all these activities into future missions to help define new missions. The core activities or the project activities that you'll see examples of, they are really contributing to these two here of defining new methods and developing new methods and new data sets, and to try to advance in science by using these data sets. So that's a core in a way of our activities and what is reflected in the projects. In some cases, if these data sets are kind of successful, if they are useful for making good science results, if you see that, then we can try to make them go further into some operational programs, like so kind of outside ESA. We are maybe part or contributing to them, but not driving like Copernicus. Sometimes our products that we develop could go into a Copernicus service or into the Destination Earth initiative of the Commission. So these are also then kind of ultimate goal in a way of what we're doing, so that we can ensure that there'll be some operations of this afterwards. So in order to ensure that we succeed in this, we are doing some strategic activities. One of them is the collaboration that we have established with the Commission, with DGRTD, where we are trying to make ESA's future EU program work together with the Commission's Horizon Europe program. So how do we do that? One of the things is that we make reference in our in ESA ITTs to projects, for example, in Horizon Europe or vice versa, and encouraging or pushing people to link with the projects of the other institutions. The goal is really to establish collaboration, concrete strong collaboration between ESA projects and Commission projects, so that they can work together and achieve more than if they worked on their own. And the kind of overall principle is then, of course, that in ESA we focus on the Earth observation part, while the Commission projects focus more on either on the in situ part or on the modeling or both, and maybe with a smaller part on Earth observation. That's the kind of principle. And in order to help with this, to work together with the EC projects, we are launching these ESA science clusters. So not only for that, but that's also main objective of them. That we already have a good sharing of information between the ESA project. That can have already established collaboration between ESA projects. Also with the same goals that we can achieve more if we put several projects together. And the mechanism for this can be both between ESA projects and between ESA or EC projects, that we can now add budget to an existing project to bring in partners from the other projects, so that they can really work on and have a work package together and work on some dedicated issue that we have established as a kind of priority issue in the science cluster. I would like to mention also the ESA Science Sub, probably was maybe mentioned. I didn't see the presentation of Jerome yesterday, but we have also this as a strategic activity, that we are trying to get the science into ESRIN. So we both have senior visiting scientists and younger scientists like postdocs. We have Karim Dush, have an example as a scientist who is working with us in the ESA Science Sub. And also this, the digital twin Earth is another strategic activity, linked a bit to what I said about destination Earth, that this can be a kind of place, the digital twin Earth, where what we're developing in this science project can be put into a digital twin Earth, and media them together as a kind of home where all different pieces can be put together, and with this we can also do simulations and predictions and simulations. So back to the cluster. The cluster we have established before today for 4 different clusters in ESA. So polar, ocean, carbon, and atmosphere. And 5 more are on the way. And this one of them is hydrology, or water cycle science and hydrology, that we're launching today. What we're trying in the science cluster is to provide input to new missions, but the focus is really on providing enhanced knowledge of the Earth system. And when we have done that, try to turn that into something useful for society, try to make some solutions with the societal benefits afterwards. We're doing it as working with the scientific agencies to try to establish joint science agendas. Example where, for example, WCRP, JWEX, Peter, and for example related in regional initiatives like INARC or HIMEX. Then we try really, as I said, this community approach to have projects working together, so we can work against more ambitious goal than one project can do. And also this that we try to link with the outside ESA with the commission projects, etc. And we try to maximize the open science, and we have established some tools for that also in ESA. Just to say that one example of a common goal that we are working together is to really represent as best as possible the water cycle. So that's a clear one identified goal. Actually, many other things that we can identify, but at least that one is a first one. Well, we have many projects we have been working on trying to estimate one variable representing one element of the water cycle, and we have other, for example, at high resolution as best as possible, often at 1 kilometer resolution, and then we have other projects where we're trying to integrate different variables, put them together. Then I would just say, just one word, 2 words about upcoming activities related to this. There will be an invitation to tender coming out very soon about multi-mission river discharge. And there will be another one related to the human impact on the water cycle. We will have a little discussion afterwards. Maybe we can discuss more about them afterwards, because I see I'm already running a bit late now. And with that, I will just say that we launched the ESA science cluster for water cycles and hydrology. Thank you very much. And then we will go through now all these different projects and have a little discussion afterwards. Thank you.
Thank you, Espen. I think without waiting, we should continue with the first presentation.
Espen, I have a comment. On your last slide, you wrote multi-mission river discharge. That is, in fact, called near real-time river discharge, and most important, flood forecasting. And half of the effort that has to be spent on this coming activity is about modeling, estimating river discharge in models, and forecasting at least a few days, like 7 days might be difficult, but maybe 5, which is very important for people who are waiting for this data to get ready for the flood, which is coming tomorrow, the next day, to take their piano to the second level, if they have a second level, or to seek shelter, or to put more bricks in the levees around the area they need to protect. So river discharge is going to be assimilated, produced, assimilated, but the most important is flood forecasting.
Yeah, so that will be on the first ITT that's been presented. So a big one to be launched.
Now it's ready. Statement of work.
It is almost ready.
TV,
a big one with
let's go.
1.8 million. So
everybody's waiting for it, especially the people who are getting flooded.
Christian Massari for the first project. So 4D Med hydrology. Stage is yours.
Good morning, everyone. I'm Christian Mazzari from National Research Council, and I will talk about this initiative focused on the Mediterranean, which is called the 4D Med Hydrology, and it's basically a regional initiative, and it's precursor of DTA hydrology, and this 2 years initiative is almost at its end, and last meeting will be next March. And I have to acknowledge the partner of this project, which is led by Siena Rirpi, then there is TUVN, CIMA Research Foundation, Observatoire de l'Ebre, Ghent University, KU Leuven, Hydroscience Montpellier, URAC Research, Estellus, and the company Planet. So the idea of the project is to try to develop an advanced high-resolution, a consistent reconstruction of the Mediterranean water cycle by specifically focusing on the use of new ESA Copernicus Sentinel missions. And so why the Mediterranean? The Mediterranean has a unique character. There are many processes happening on a local scale, high climate variability, and is considered a hotspot of climate change. Also, it is exposed to many hydrometeorological streams like flash floods, landslides, and there are strong interactions between these small-scale processes and human activities, and that require actually Earth observation at a very high resolution. So there is an observation gap on the Mediterranean that requires the use of Earth observation data at this scale. So the 4D methodology can be considered like a joint from previous core scale activities focused on the water cycle from ESA and new DT hydrology initiatives. And then he tried to actually complement this gap between the two. The idea is not only develop products at the resolution, but try to integrate them in a consistent manner. So the idea is to use different satellites, possibly at high resolution, and try to develop the different products in a synergistic way. And so these are the list of the products that we developed, and basically are all the components of the water cycle. We have also different versions of them. And the idea is to try to make them more consistent and to reduce the uncertainty by water balance closure techniques that Philip highlights, for example, in his expert office, its responsibility in this project. So we have 28 domains for the Mediterranean. We have daily data and 1 kilometer grid. And basically, we exploited many resources for developing this product. We used the network of resources from ESA, so I have to thank them for this. And basically, the idea is to provide the data. But before to provide the data, we need to validate them. So what we did basically is to select the 4 different areas in the Mediterranean. And in this area, we collected a lot of different ground-based observation to validate the products. And this is the database that we built, and basically is available. Some data are not freely available, but can be requested. But these were very useful to understand the quality of these products. All the products are available. We provided a Stack platform where you can download the images in GeoTIFF, and there is a platform where you can visualize the product. This is, for example, the soil moisture developed by 2VN. And so all this data can now be used. And there are the links that you can check online. Using this data also, so we want to demonstrate how that this data is useful for science, and we envision, sorry, the slide are a bit confused, but we envision 4 science cases. One is the reconstruction of, so how much snow there is in the Mediterranean basin. There is a poster from Francesco Avanzi that you can look at the poster session. Land atmosphere interaction that actually run by Diego and his group. And also the human impact on the water cycle by assimilating Sentinel-1 backscatter and snow, and also try to understand the source of for irrigation water. Then we have different applications for society, for improving the resilience of society, which are agricultural drought monitoring and water source in the Ebro River basin, and also flood modeling and landslide forecasting in some places in the Mediterranean. So this is the website, and you can find some more information there if you're interested, or contact me. And just a final slide to say what we learned from this project. I have to say that developing products together is very challenging. So one idea, I mean, that I propose here, but something in this direction is already running from ESA, is create a unique platform where just sharing codes, data, and models all together in an open science. And this is what we envision also in a publication that we published in the 2023, which is about creating an open digital twin Earth hydrology infrastructure. And another thing very important is that we need to address the problem of ground observation. So identifying in a common way different CalVal site where we validate that the different products would be also an asset, I think, for these water cycle activities. Some ideas about the future direction, especially for the Mediterranean region. We realize that daily resolution sometimes is not sufficient, and probably missions that would increase the temporal resolution of, for example, passive microwave products would be very important for water use for humans, or understanding the daily cycle of vegetation and the atmospheric interactions. I can think of flash floods and so on. And finally, also the satellites for activity for river discharge runoff and groundwater is particularly important, because especially groundwater, I mean, is hidden below the surface, and it's very difficult to have information, especially at local scale, on this compartment of the hydrological cycle. Thank you. This is, if you have any question, back to you.
We have only time for a very brief question and potentially brief answer. If no, then we continue with the next speaker, which is Luca Brocca from CNR for the project DT Hydrology Platform.
So good morning. Oh, full room now. I will not acknowledge all the people because I have only 5 minutes. I have 2 videos of 2 minutes, so basically the time is already done. If you were here yesterday, you have seen already something. If not, this is what we have done in this project called Digital Twin Hydrology. That was kind of 2.5-year projects, 2 slots, and the idea was to integrate high resolution Earth observation and advanced modeling for coping with extremes and also water resource management. The video actually shows by itself what we have done. We have done the activities for the full Mediterranean area, and actually for this area we have developed satellite data for precipitation, evaporation, soil moisture, snow, water equivalent, and runoff, river discharge. And we move from the 20-kilometer scale that was available up to 5 years ago to 1-kilometer scale. For doing this, it's a big effort from many partners, but actually the output was really good. Basically, the project presented by Christian before was, it's a kind of new development of the products that was originally developed here. So it's a kind of sister project or brother, I don't know. And then we have used all this data together with modeling. And so, for instance, we have done simulation for flooding. Here in the video, we are going to see the simulation for flooding in Sicily during the Medicane that occurred in October 2021. Yes. And this is done, actually, the flooding simulation now is run at 5-meter resolution. And we then compared also this simulation against the Sentinel-1 flooded area to understand the quality of the simulation and also the quality of satellite data. And the last things that we have done is the what-if scenario. What-if scenario is basically a way for putting all this stuff all together and making it available to the user, to the decision maker, to make it easy to understand. This what-if scenario for flood risk is basically you can set up, there is a platform that I'm going to show you in a minute, in which you can select precipitation and soil moisture, the 2 main drivers of flood, and then you can see how the flood change along the river. This video has been carried out by, it's been developed by a company in the US called Planetary Vision, and the acknowledgement. So basically the idea is that now, but not only now, in the recent time, we are struggling with extreme events over the Mediterranean scale. Here, just a couple of them, but for instance, Storm Daniel is the last one, but actually we had in Italy another one a week ago, 2 weeks ago in Tuscany, and that's always the case. Data infrastructure is important. This platform has been already shown by Christian. Actually, the high resolution data by itself have no use if we don't build also something to make them available to the people. This data infrastructure platform is by System Data Lab. Basically, they did actually these activities are done in a kind of few projects, not just a DTE hydrology project with ESA. And this platform, you can really download the data, extract the data, work with the data very easily and very fast. You can click on a point and you have suddenly the data out for 1 point for 5 years for precipice almost, and that's very fast. Nothing with as compared with the other. And this is related to how the data are stored, basically. This map I've done by myself, and I'm not expert in Python at all. And then the front end is this digital twin platform that basically you can go online. Here the link is not there, but probably later. I don't know if I don't remember if I put there, but it's open and there are 4 buttons. There are 5, but the 4 button is the first one is for drought assessment. And basically you can, the data at monthly scale for anomalies are plotted for the full Mediterranean scale. Precipitations and moisture evaporation. You can compare the data by them. Among them, you can have this kind of plot showing the current status. For instance, in here we are showing October for precipitation was, I guess. Flooding, you have already seen, but there are 2 case studies. One of them is the flooding for Sicily. There is another one in northern Italy. You can explore the data. You can actually look at the data, extract the data points, and you can really see how the flooding area change over time. What is scenario for flood risk? That's very easy. The background is very complex. Many people work together to integrate the data to provide the data of satellite precipitations and moisture modeling, all these kind of things. But then at the end, we have a platform in which you just click 2 points, you have 2 boxes, you change 2 numbers, and you have an output of the flood evolution along the river. We have picked up some points, but you can really see how flood risk change depending on this condition. And finally, what is scenario for water resource management is even more complex. Here we have 4 different options for initial soil moisture, initial snow, forecast of precipitation and evaporation. And the most important things here is this line of graph in which actually you can see the water use over time for the next summer for the Po River. And actually you can really see if there can be some deficit for the water usage. So for instance, now there is no deficit, but if this giant line is below 0, means that we are going to have a problem during the next summer. If you were here yesterday, this is the last slide, I guess, yes. And everything seems to be done, but it's really far from here. It's just, for instance, you have seen just case studies for prototype for the Po River, for the Med. But if you want to go global scale or even European scale, still a lot of things to be done. These are the 5 challenges that I have considered. Yesterday, I make a kind of overview of each of them. Basically, the slides for yesterday will be available, but if you have any kind of question, I'm here for up to Thursday. And we are working on all these topics in not only ESA-based project, ESA-funded project, but also from European Commission and from EUMETSAT, basically to try to address these different problems and to try to make our science closer to the society as best as we can. Thank you very much for your attention.
Thank you, Luca. Any questions? Yes, please.
Thank you for that. Well, the 5 challenges, the pressure temperature versus sample. So I understand in order to keep this at a very high spatial resolution, mostly very cost, high temperature is the weight cost, and especially data you show that from 20 grams to 1 gram. So if we want to do any hints by how can we bring it down to the spatial resolution?
Of course, with satellite data, it's always the case. You have to select either high spatial resolution, either high temporal resolution. Then, if you launch kind of a number of satellites, you can try to start to getting high spatial and temporal resolution. So, for instance, precipitation is high temporal resolution because it's kind of constellation of, I don't know how many sensors, but a lot of them. And this is one of the points. So basically, one of the points is this. Then there are, for instance, some call for Earth Explorer in the future in which you can have some kind of new mission with high temporal resolution. That is one of the main points. Actually, going in hydrology, if you go to high spatial resolution and you don't go at the same time to high temporal resolution, is probably no need. This is one problem. But the second problem is most important, that there are a huge number of data sets at high resolution in space and time now published, for instance, for most precipitation almost. And if you look at the data, they are not at the resolution that is claimed for. So that's why I'm saying resolution versus sampling. You can sample everything at even that centimeter scale, but then we have to see what the data are. And then once we want to use the data at high resolution, so for instance, if you want to use in agriculture for irrigation, for instance, if the resolution is not the one that is claimed, you can easily see. And this is something that we have to address. This is science, of course. Somebody has to do this, because otherwise it's really just confusion and everybody's saying, okay, I have the data, but that's high resolution, but it's not. And we need some guidance along all this world of machine learning and modeling and blah, blah, blah. Done.
Yes, thank you very much. Thanks, Luca. I'm pretty sure we can further discuss this question in an hour or so. Then I call Philippe Perez from Estelus to talk about the AI for EO water.
Okay, so oh yeah, this one. It's not. Do I need to put in?
Yeah.
Yes, this
Full
one.
screen.
Okay.
Now it works.
Okay, thank you. First of all, I would like to apologize because basically I was supposed to do this presentation yesterday night. I had the technical issues. So basically I did the presentation this morning in the bus, in the way coming here. So, okay, I'm going to present you some approach to introduce some physical constraints into artificial intelligence methods. So you probably see my presentation about closing the water budget yesterday, and we had seen some example of this kind of application in the 4D Med project. And we want to investigate if we could use artificial intelligence in order to do this type of things. So what we have done so far was to use, we don't have any pointer for, oh, it's okay. Okay.
Mouse or not?
No. Okay.
Can you go to the other screen?
Other screen.
Go to screen.
Oh, it's okay. It's okay. Don't worry.
Normalement, on peut passer.
Okay, it's okay. So what we used to do is to use optimal interpolation. This is a technique that you might be familiar with in different basins over the world, and to close the water budget on that. But we had the strong constraints. For example, we need to have river discharge in order to do these kind of things. And river discharge is very difficult to obtain at the global scale. So that was a big issue. How to go from these selection of basins to the global scale. And this is why we wanted to use artificial intelligence. So you see here on the top a paper that we did in 2014 about possible ways to do that. You see the inputs with precipitation, groundwater storage, evap, etc. And we try to optimize to have something which close the water cycle. But basically here, this is very crude and simple, and we cannot introduce constraints that are strong constraints. And this is why we decide. Okay. Yes, okay. So this is very crude and simple, and we couldn't really, we were not satisfied with that. So the idea of this project was to put some features here inside the neural network in order to obtain something that is useful for us. The things that we have seen with optimal interpolation is that we need some of the features that are described here. So for example, we need modularity. We need a process of the satellite data that, for example, first do calibration of the data, then do data fusion, and then integrate the water components together in order to close the water budget. And we try to develop a neural network that is able to do that. So this is deep learning, is very innovative. You don't see so much things like that, and it's very difficult to set up, actually. The optimization, the training stage is very difficult to perform by doing that. So this is a preliminary test. We did some learning over some of the basin around the world. We train a neural network using this kind of techniques, and we have done some, so you see here, the decrease of the budget closure imbalance. So it's not perfect, but yeah, we didn't have so many basins in order to do the training at the global scale here. And the things that we can obtain from that is some kind of bias that we think there is in the satellite data. So for example, here for the EVAP, we identify, this is a feature that we see very often, some bias estimates on the EVAP, and some uncertainties also into the estimation of the EVAP. So the full process is this one. So I showed you before with 15 basins, we are actually using more than 2,000 basins around the world in order to do the training of this method. I cannot go into the details, but we have a different neural network for the training stage and for the application. And you see here how we close the water cycle with this feature. Here there is a physical constraint inside, so you have the water balance that is represented here inside the network, and you ask him to have 0. So this is a standard feature. This is less standard, and also the full architecture try to represent what we want to do. So from that we obtain the best compromise for the water components that are represented here, and something that is very useful. I think this is very useful. We have the systematic bias for all the products that we have integrated, for all the 4 precipitation data sets, for the EVAP and the groundwater storage from GRACE, and the uncertainties also. So I think that for the data producers, that could be useful. They can compare with the other data sets and regions that seem to be not coherent with the other water components or not. Okay, so we did 3 papers. One is about the methodology on this. So it is representing these results. We have also a paper that tries to identify some kind of patch to correct some of the data set. This is an example for the EVAP from GLIM. And another paper that is about the closing of the water cycle at the global scale. So to conclude this presentation, I think you see that in some of the disciplines, artificial intelligence is really doing a big revolution. You see that with the weather forecast, it's completely disruptive for science. In hydrology so far, we didn't see a lot of applications of artificial intelligence, but it's going to be a big change. For example, for river discharge, there are some specific algorithms like LSTM, long short-term neural networks that seem to work very well and that could work at the global scale. So it's going to be a big revolution. So we have 2 ways to do that. Should we compete between the physical models and the machine learning models? Is there a competition between these 2 things, or should we combine them? So what we tried in this project is it's a first stage to introduce some physical constraint inside this kind of machine learning models. And I will stop here.
Thank you very much, Felipe. You just pinpoint one of my last slides on this topic of
Okay.
AI and machine learning. I think that will be yeah, food for thought and discussion.
Okay.
Any question?
Yes?
Yes, please.
This model state already close to water balance.
Yes.
Secondly, is the added value of this machine learning which your price to load balance based on
So this is attempt to close the water budget, so only using satellite observation, so that you could use in order to calibrate and assimilate the data into the models. So it's good to have a description of the water cycle that is purely observational. Also, what we have shown by doing this kind of things is that we are able to extract more information than originally was included in the satellite observation. So by doing disclosure, for example, we can downscale the grace data from 200 to 1 kilometer. We can do daily interpolation when you add much coarser. So by doing this integration, you improve your knowledge of each one of the individual products.
it's not predicted in rank right here at zero.
Mm-hmm. Yes, Grace is integrating everything.
This product it's not predicting the difference.
No, but we could, if we had enough information about each one of the components, we could integrate that into the framework to describe the components inside that are measured by Grace. The big difficulty is underground water storage. We have seen a presentation from Fabrice, so the student of Fabrice Papa, that we have Grace, and then by estimating the surface waters, we try to estimate the underground water. So this is that shows you that you can maybe by integrating the data together, you can have access to some of the missing information.
I'm afraid we have to move on. Sorry, but we can continue again this discussion in an hour or so. So now we welcome Angelica Tarpanelli for Stream Next and Demetras.
So good morning. String Next and Demetras are two new projects that will be launched. One was launched 2 weeks ago, and the other one very soon, I hope. But before to speak about that, I want to tell you the path on which we arrived to these two projects. So what came before? In 2018, we as a ERP group, we won this open call called RightSat for the river flow monitoring and discharge estimation by integrating multiple satellite data. The purpose of this project was to merge the information coming from altimetry, multispectral band, and thermal band in a unique solution, in a novel methodology for estimate river discharge, especially in engaged basins. And in collaboration with DTU Space in Denmark, we reach very good, successful results with estimation of river discharge quite accurately, but only with the use of altimetry and near infrared. So the thermal band were not so good. The next year, we won another open call called STREAM, satellite-based runoff estimation and mapping. So in this case, we are talking about river discharge, but distributed in the basin. And in collaboration with Stuttgart, and we develop this conceptual hydrological model for deriving runoff estimates from satellite soil moisture, precipitation, and terrestrial water storage anomalies. The project will be developed, the approach will be developed in 5 big basins in the world. And also in this case, we reach very, very good results. So the two approaches are slightly different, no? So we have stream that is that give us the information distributed in the basin, and we have RightSat that has that provide us a local information over a basin, so more punctual. So we continue to study these two different approach, and we try to merge all together, integrating these two for the main objective to estimate river discharge. And what we have done is to improve a little bit both the approaches and testing over two big basins, the Mississippi and the Amazon. Also to solve the critical aspect of both. And what we get was the improvement, of course, of the two approaches by the integration. So this is the story. And what we have done now with Stream Next, for example, that is led by Stefania Camici from IRPI, is to try to go at global scale first, and to provide long-term gridded runoff and discharge estimated only by satellites. Our second objective is to understand how much the resolution of the gravimetry data affect the model results. So will be also some aspect linked to the potential of the new MAGIC mission. And third objective is to analyze the standardized runoff anomalies to evaluate also the impact of climate change. With the MEDRAS, the situation is slightly different because in the 4D Med project, we realized that the RightSat approach that we developed was not so good for small rivers like the ones in the Mediterranean area. So the approach here is to increase to try to improve the methodology, also to estimate and monitor small rivers, trying to give a daily discharge by using also another methodology that is the machine learning, several machine learning schemes. So actually, what do we need? First of all, the accessibility of data. On this respect, maybe we fail because all these data set on the approach and so on are in several places. So what we expect, I think the community wish is to have one common box in which you can download all this data of river discharge or the method, the code. Of course, it's very, very important the cooperation and the synergies with other projects. So the approach of RightSat was implemented over several other ESA project, and will be used also in an Horizon project. And for Stream, of course, will be used also in the MAGIC project that is funded by ESA. So it is important to create this kind of link. And about the priority issues, I can say that the global application for both approaches is quite important because the river discharge is a variable very difficult to estimate. So there is the need to have this kind of data. And of course, we need to analyze the engaged river basins where we have more that are quite very, very important. And then I think there is also a need to give this data set of river discharge from satellite because the ground monitoring is not sufficient enough for the model calibration and assimilation. So it is important to integrate this kind of information also in the modeling. So that's all. Thank you for your attention.
Thank you, Angelica. One question, one short question. Yes, Felipe.
Okay, so you have different methods to estimate river discharge. Can you estimate in engaged basins, and how do you see doing that?
In the in the stream next, the target is to go at global scale by regionalizing the parameter that we find in several basins, gauge basins, and to apply the same parameter in engaged basins. With the right set approach is a little bit more difficult, but in the future we can try to go at global scale by looking at the same approaches. No? So you go to the regionalization of the parameter that are used for the estimation of river discharge, and then you can go globally. So these processes are ongoing, and of course, there is a big margin of improvement.
Thank you very much, Angelica. So we move on with the Hydrocoastal project, introduced by Karina Nielsen from DTU. Sorry. It's fine. No, it's not. It's the service view, sorry.
Is it a PDF?
Yeah.
Yes.
So you have to, you have.
Full screen mode.
Yeah. Okay. Should it work? Yeah. No?
No?
Yes.
Oh, if it's not full screen mode, I cannot.
No. Yes.
We have to go to
This one?
no, WebEx?
Mm-hmm. No, but it's not for WebEx. It's the problem is that it's a PDF.
Yeah, but we have to mirror the screen. Yeah.
Oh, when we put full screen.
Okay. Mirror the screen.
Because it's
Okay. Duplicate.
Okay.
Thank you.
but it's
So
And,
you did it with a keyboard shortcut. So
okay. Okay.
thank you.
Okay, so sorry about that. So yes, so we have on the whole hydrocoastal theme, I would like to introduce this project. So as you can see here, the hydrocoastal is about improving SAR altimetry and processing over inland waters and coastal zone. And due to the interest of time here, I will focus only on the inland water part of this project. But just to let you know that there's an equivalent coastal zone part. Okay. So to present the objective and an overview of the project. So the Hydrocoastal project has been running for the past years and it's actually ended now. But the main object of the project was to maximize the use of SAR altimetry for inland water. And with that, we have in the project developed an entire processing chain from the level 1A all the way to discharge. The project was run in a way that it was running in two phases. The first phase was to develop the chain and test different processing algorithm. So regarding retracking, so once we have the waveform, we tried 3 different retrackers in the project, and then we developed so we could make time series of the water level. And in order to make these time series, we used various, we used the SWORD database to figure out where the rivers are. And then we used the occurrence product by Pakel also to extract the water over the rivers and also lakes. And then at the end, these water level time series we used to make discharge. And also regarding the discharge, various method was presented. We use a Manning approach, the approach presented in the right set, and also rating curve approach. So in this first phase, after the first phase, we did a lot of validation by different teams. And by that, we selected the best retracker for the project. And in this case here, it was the retracker that had the overall best performance. Not that it was the best retracker in all cases, but overall best performance. And with that, we selected the BTU retracker. So in the next phase, all the processing chain was run on the Earth console, which greatly improved the speed of the processing, because if some of you have tried to download these level 1A data, these are large volumes, so it greatly improved the speed. So the outcome of the project was a global data set where in most of the cases, so here on the map you can see the different rivers that was processed within the project. And if you can see, there's a sign saying level 2, level 3, level 4. So for the different rivers, you can see the different levels of data available. So once we had our global product, and there's a link there to the data, that's where you can go and download the data, so they're really available. So once we had this product, there was done a lot of impact assessment studies to assess the added value of these new products. So regarding the inland water studies, there were 4 different impact studies, one to assess discharge, and also one that assessed flood and drought risk on the Po River. And actually, Angelica will do a presentation about this tomorrow. Then there was assessment over Irish lakes, and also discharge and water level assessment over the Rhine River, and also hydraulic modeling over the Amur River. So with this big project ended now, we of course have gained a lot of experiments and a lot of things we would do different, and a lot of new things we would like to try. So here I categorized our recommendations into, so you can see different, the different categories here. For example, auxiliary data. It is very important once we are dealing with both rivers and coastal zone that we will have a consistent reference surface that are the same for the 2 different surfaces. Then it would also be very convenient to have ice flag telling us when there's ice on the river or lakes. So also some recommendations for the processing chain. For example, it was a great speed up to run the processing chain on the Earth console. So putting our modeling into the cloud where the data is should be a waveform. So we would also recommend to use maybe different retrackers for different surfaces. It could be either by waveform classification or some other intelligent way to figure out what retracker to do. Then, since this was a very big project, where validation was done by different teams, we recommend to have maybe a more direct or maybe more structured way of doing the classification. And then also, once we have the product, there should be a clear way of how should these be continued so that the knowledge will not be lost. Then again, for regarding maybe some new studies, could be to maybe exploit a bit more the fully focused SAR or 80 Hertz over small targets. And also do more investigations in this interface with the river and the coastal zone, and understand the different parts of the signals that we see. Then maybe also having a sandbox tool where we can demonstrate flood and drought and show to stakeholders to improve also this. And then of course now where we have SWOT, we recommend having studies on how to integrate all the media altimetry with the SWOT data to make even better products. Maybe some recommendations also for the agencies is that especially when we are studying very small targets, it would be beneficial to have a better constraint on the orbit because even with Sentinel, the orbit from one repeat to another can be maybe a few kilometers away from each other. And then maybe also to improve more the temporal resolution would be to have this constellation of many small satellites so we can get a better temporal resolution. So, and to maybe some recommendations for new product could be to have these easy accessible data sets that could be level 2 or other levels so that it is easier for the user to get the data. So yeah, this is just the same in a more condensed form. But so with that, I will just say thank you very much. And there's a post about the project. So if you have questions, you're welcome to come and talk to me. And also here there's a web page where you can have access to the deliverables and many, many more recommendations also on coastal side and more processing. So thank you very much.
Thank you, Karina. One short question.
And if you want to know more about what Karina said about computing system data infrastructure, she mentioned the Earth Console. You go and check poster number 24 on the first floor.
Yes, a small question. Can you estimate surface waters below vegetation?
Yes, so for example, if, so with the radar, we are able to also see what's below the vegetation. But of course, it will depend a lot on the size of the target, but that's where we can maybe go in and use the fully focused SAR instead, because then we'll be able to look at much smaller objects.
Okay, and a second part of the question. So you mentioned you have a global product, but it's some regions that you have around the world.
It is not, unfortunately, there were not resources to do all rivers, but we try to have like large rivers, small, medium and small, and also in both in the Arctic and in the arid and in tropical regions. So that is.
When do you think a global product from SAR will be available? Because we already did the data fusion of visible, microwave, and different and maps of surface waters. But what is missing is a SAR data that would be at the global scale, and
Yes.
we are still missing that.
Yeah. So okay, one question. Maybe are you referring to image SAR or SAR altimetry when you say?
Yeah, mostly image SAR.
Okay, so yeah, so we didn't use this in this project. So here it is SAR in satellite altimetry.
I'm afraid we'll have to stop the discussion here and move to the next one.
So I'd like to invite Thomas Nagler to present to us the AlpSnow project. Please, Thomas.
Okay. Thank you, Espen. In this short presentation, I will give you an overview on the AlpSnow project, which is on the development of innovative methods and products for monitoring physical parameters of the seasonal snow, focusing on the Alpine regions, only on the Alps. You see here below all the different institutions and organizations contributing to these projects, including organizations dealing with the development of methods for retrieving snow parameters from microwave and optical satellite images, but also organizations using these data sets in their models in science applications, but also for in pre-operational or operational organizations. The AlpSnow is a science activity within the ESA Alpine Regional Initiative. The project actually deals with the development and demonstration of innovative satellite-based products serving scientific and operational needs in Alpine environment. And it's actually what we want to do is to go towards the bleeding edge of the methods and algorithms, what we can do in order to retrieve a set of consistent physical parameters of the snowpack. And we are here looking for snow, also for the use in snow process and hydrological modeling. And one of the major goals is at the end to support the regional operational priorities in hydrology and water management, but also the science community in order to work on the assimilation methods to use this in various snowpack models and hydrological models. The project started in December 2020, and this the baseline project is close to the end, but we are continuing in a couple of further activities until the end of 2024. Now, what did we develop within this product? So we were looking to the complete set of physical parameters, including the snow extent, surface albedo, grain size, wet snow extent, looking for the liquid water content, also quantitatively, and snow water equivalent, and also to the snow height. And we discriminated here at the end two type of products. Ones we called pre-operational products. They are in a quite mature state, and we were able to generate a 7 to 8 years time series of products over the Alps, which is consistent and validated and also attached with uncertainty information. And this is, we were relooking the fractional snow extent from Sentinel-2 and Sentinel-3 and also tested other satellite data. Important was that the high resolution data set with 20 meters are consistent with the quasi-resolution data set, which is about 300 meters, in order to merge them, because 20 meters is available sometimes and gives every couple of days, but gives a very good detail in the complex terrains of the Alps. So topography, but also, of course, surface types. On the other hand, we need also the temporal view, so the kind of daily coverage would be needed. And for this, we are using the quasi-resolution. And to use both of these, we developed new algorithms exploiting not only a few bands, but the full spectral capabilities of the sensors, and also account for the non-shaded and shaded regions in the Alpine terrain, which is, of course, a general problem when you look to the more conservative algorithms. Surface albedo and grain size was done with 300 meters resolution over the complete Alpine terrain also, and is based on an approach from Binder and al., already published a few years ago, but was further developed and dedicatedly adapted for mountain regions. Wet snow was done with SAR data. We actually also looked into the quantitative estimation of the liquid water content in the snowpack, but this we could not achieve this. There's physical limits actually of the duality between surface roughness and the liquid water content, and this was not possible. So we stayed with the kind of wet snow extend product, what you see here on the lower part. But it was extended with a kind of demonstration product. We were actually trying to identify very accurately the different melt phases of the snowpack, which works quite nicely on the early melt and then when the snow cover is broken. But the Sentinel-1, actually, it was not possible to really look into details of the melt refreeze cycle, which is on a daily basis, so morning versus afternoon overflights. This is only partly successful, and we would need actually a different sensor, and there was one proposed already in the Earth Explorer 11, again reproposed in the Earth Explorer 12, which is a geostationary SAR system, which could really provide on a daily basis to follow up these parts. Then for snow water equivalent, we followed two approaches here. One was a model snow water equivalent. So we had a snowpack model from the Geosphere Austria, and they were using Earth observation products and assimilated those into the snowpack model. And it's a physically based estimation with over the Alps of about 100 meters resolution. As a demonstration product, we are looking here for snow water equivalent from L-band. Demonstration products were generated using pulsar and SARcom data over the Alps, but it's not on the operational state yet. The physics of this method is very nice and it's well understood, but we need the right sensor in space, and very soon in the Q1 next year, we will become NISAR from the US and Indian Space Agency. And later on, of course, Roselle in a couple of years, which will be an excellent sensor. And this activity was carried out in preparation for these two sensors. And hopefully we can then start quite soon in order to produce these products. Then snow height at the end of the winter period means at the end of the main accumulation period, just when the snow starts melting. And here we developed a very new method, which is called neutral calibration of single pass interferometric tandem X DEMs and Sentinel-1 SAR. It turned out that when we used the standard DMs from Tandem X, there were still some phase tilts due to baseline errors, and it was possible finally to recalibrate this. And we are just looking into these very accurate DMs, what we can get out in terms of snow height. So this is still going on. And this activity is not standing alone for Tandem X, but we are looking forward to Ka-band radars, which will come quite soon and will be the excellent tool for monitoring snow height. Now we exploited this very quickly because Espen got nervous. In the science cases, there are 6 cases defined, and you can look this in various cases. So there is University of Edinburgh, University of Innsbruck, and SLF in Davos actually using these maps. And just to let you know, there was a very significant improvement in the assimilation and also in the learning how to improve the models. For example, what you see here as an example in Switzerland. So if you need more details, just reports are or will be made available quite soon. As a summary, we have new and improved algorithms for retrieving the physical snow parameters from SAR and optical data in mountains terrain. We have a 7-year time series, almost daily, depending on the sensors used on snow extent, albedo, wet snow, and assimilated snow water equivalent. And this was the input for these cases. Then we have demonstration products for these remaining other parameters. And we use those in the scientific use cases. Some recommendations. We tested this for the Alps, but we want to go to other regions around the world. We are coordinating already with INARC and supporting them in this common observation period, which is just running. And this is a kind of win-win situation. So we are providing the products to them and getting very good validation data on the other side. Then we have further development and retrieval algorithms on open issues on the various products identified. Then there is quite important, we need further R&D on the assimilation of these EO products into the various products. So we are not at the end here, so we just started. And especially one issue is that if there are more EO products from different parameters coming into one process models, we need a kind of homogenization and a proper uncertainty qualification. And there is some cooperation synergies or potential input to various other projects like Digital Twin Earth, AI for snow, and contributions also what we are giving towards future missions in order to improve them and adapt it for snow research. Thank you.
Thank you very much, Thomas. I'm afraid we don't have time for question now, but you can ask Thomas afterwards. Then I would like to invite Jacopo Dari to talk to us about the Irrigation Plus project. Please, Jacopo.
Okay. So good morning, everybody. I am Jacopo Dari. I work at the University of Perugia, and I'm also a research associate at the CNR IRPI, which is based in Perugia as well. And I'm glad to present the Irrigation Plus project, also on behalf of several colleagues that of course, were involved in it. Before starting, maybe it's good to point why it is important to study irrigation when dealing with the water cycle. Basically, because among the human activities that somehow interact with the water cycle, irrigation is the most impactful one. So basically, we cannot neglect this variable, which is actually can be considered as an hydrological variable when dealing with the water budget over anthropized basins. And this was actually the driver of the Irrigation Plus project, whose aim was to develop Earth observation-based algorithms and techniques to monitor irrigation. When I say monitor, I mean detection of irrigation, so in space, in time, and also the quantification of irrigation amounts. The project was led by CNR IRPI with a consortium also made of ELIF, SPIRE, TU Vienne, Toulouse University, Ebro Observatory, and KU Leuven, and was very fruitful in terms of publications of datasets and results produced, and outreach activities and so on, but we will see in the next slides more in detail. So we had 6 pilot areas in which we collected information on selected test sites in Germany, South Africa, Spain, France, Australia, and Italy. Over these test sites, we collected in situ data about irrigation dynamics and, of course, also remote sensing datasets useful as an input for our algorithms like soil moisture, evaporation, and also other Earth observation-based products. So coming to the results, we developed several datasets of irrigation amounts, several datasets because they were produced with different approaches, and for each approach for more than one test sites. Here, for example, these slides summarizes the products developed with the soil moisture-based inversion approach developed at CNR IRPI. We produced 1 kilometer irrigation estimates over the Ebro in Spain and the Po basin in Italy, and relying on Sentinel-1 soil moisture. And also we had a product over Australia, Murray-Darling Basin, at 6 kilometers, relying on Cygnus soil moisture produced by SPIRE. Of course, we have also irrigation amounts estimated according to other approaches implemented in the project, like, for instance, the soil moisture-based delta from TU Vienne, the data simulation approach from CNR IRPI and KU Leuven, and also for an approach based on evapotranspiration developed by ELIF. We have also mapping and timing, so the detection of irrigation approaches developed in this case by Toulouse University. We have irrigation maps at very high resolution based on Sentinel-1 and Sentinel-2 over the Po Valley, Italy, and Ebro Basin in Spain, and also a timing approach developed by French colleagues that has been implemented in several test sites across Europe among the test sites of the project. This is a slide just to recap all the products. So all the products that are in the domain of the estimation of irrigation, in the irrigation mapping and irrigation timing, with the approaches used to develop the temporal coverage, the resolution, and so on, all the details. Some of them are already freely available, as for instance, the one developed by the soil moisture-based inversion, which are in Zenodo and they can be downloaded and use it. Then quickly, for assessing the impacts of these novel irrigation products, let's say, we implemented 3 demonstration cases and 3 science cases. Among demonstration cases here, as an example, I'll show you what we did about water resources management in the Pianura Padana in northern Italy, where we basically compared our estimates. So what we can estimate from satellite, with in principle should be actually actual water use, with irrigation advices provided by water managers there through a system which is called ESA-ESRIN, to understand the differences that we still have on between what we estimate and what they suggest to the farmers. And we have also 3 science cases. And here, as an example, I'm showing what has been developed by the Ebro Observatory about the irrigation parameterization in land surface modeling, in which basically the developed products of the project have been ingested into a land surface model, and effects on the water cycle have been assessed, and also irrigation from our data sets have been compared with those of the model. So, of course, there are synergies with other projects from ESA, as for instance for the MED that was presented by Christian at the beginning of this session, in which we basically implemented again the soil moisture-based inversion approach, and we extended our estimates to other basins, like for instance the Megerda and the Gerol. And coming to the conclusion with the last slide, with further topics for investigation, we believe that novel projects could trigger a number of short-term and long-term activities in the domain of irrigation with respect to the water cycle, of course. Among short-term activities, there is for sure the further extension in space and time of our irrigation retrievals, but this is something that we are already doing in other projects, as mentioned before. The testing, of course, of novel high-resolution data sets, and also the intercomparison of several approaches to develop irrigation information to understand differences and synergies. And among long-term activities, there is of particular importance to me the construction of super site for irrigation monitoring, where irrigation is monitored in a scientific and systematic way, the improvement of our products, and also the full integration in somehow with models. That's it, and thanks for the attention.
Thanks a lot, Giacomo. Do we have a question? Yes, please.
Yeah. Yeah.
So you guys satellite information. So I know you it's not
This was the actually next step, but so far we do a first comparison with people from Canale Emiliano Romagnolo developing ESA-ESRIN. Yeah.
it's not remote sensing based. No, I was going to ask.
Yeah. No, people developing ESA-ESRIN would like to. There was this idea of ingesting Sentinel-1 soil moisture inside, but actually still not done. It was kind of second step of a first comparison between what we estimate and what do they advise.
Okay, thank you very much. Thank you, Jacobo. Then I'll invite Francesco Desan to present us INSAR-based soil moisture.
This, I guess. Okay. Yeah, so this talk is about so good morning. Yeah. This talk is about the METRAS project, which is starting soon, and in particular to about the soil moisture part, because there was another part which is already presented by Angelica before. And this part is about getting soil moisture from INSAR, so from SAR, but from the interferometric part, not from the backscatter, but from the phase.
And well, I have one slide here just to illustrate the idea. It's based on closure phase, which is a particular observable in interferometry. And but this closure phase mixes up 3 dates altogether, and the whole inversion problem is getting every single date separated, like here in this Namibia example. And you see somehow how it works. Just maybe the one important point to understand is the complementarity that I see between the phase and the backscatter. On the left part of the slide, you see the say anomalies of backscatter time series from ASCAT compared to the ERA 5 land from Wolfgang Wagner's paper. And you see there are some areas in the world where the backscatter series doesn't quite follow the soil moisture, and it's especially very dry regions, arid areas where we think there's some subsurface scattering coming from deep beneath the surface. And on the right, you see the coherence, the INSAR coherence, the interferometric coherence from Sentinel-1 in the summer in this case. And you see where we have nice areas. We have areas where we have a lot of coherence. These are the white areas. And you see there's a lot of complementarity, that when we have red areas on the left, we have white areas on the right. So, and this is not a coincidence. Basically, interferometry works where things are pretty dry or not, the coherence is good. So this means there's not so much vegetation or things are rather stable. So there's no, it's not really a coincidence. Okay, this is just an example of one case where you can see the advantage of using interferometry. On the right, you see a product based on interferometry, on always Sentinel-1. And on the left, you see that for the same dates in Libya, the backscatter change. And you see that it's much more difficult to understand what's going on. You see that in the same region, on the left, you see something is going on, but things are not so clear. Sometimes the backscatter goes even down, instead of going up as it should. And the shapes are not as well delineated as here. So in this project, we are staying around the Mediterranean basin for several reasons, but also I think it's not a bad choice. Looking at the coherence map here, you see different levels of coherence, so which correspond to different types of land cover. So we will have areas with high coherence, like in Libya, as I was saying, in some intermediate things, like in Spain, Eastern Spain. Sorry, maybe I can just go. And we have maybe, if we take some areas like the Po Valley or other places, we will have not so much coherence, so we expect the technique not to work there. And maybe Greece will be similar to Spain, and we'll see. The project is not started yet, so we still have to discuss about all this. And there's also some issues about temporal coverage. For some sites, we will try to see if we can do 3 or 5 years of products, and but we have to consider the loss of coherence. That somehow we cannot make very, very long products. We have probably to do some smaller chunks and then stitch them in time. To have an idea of what we have already seen, we want to compare the INSAR-based soil moisture product with both probes when available, or other satellite or modeling products to do some sort of cross comparison. And we see here in this special case where scatterometry or intensity-based products have troubles. On the left, you see they don't match quite well with, for example, ERA 5. And radiometry and interferometry are much better in this case. So this kind of models can be very nice because they are covering everywhere. Of course, probes are more limited in space. And CNR-ERP was already doing some first comparison between many products actually. But if we look at the yellow box, we see the INSAR products compared to SMAP and GLEAM with a rather high correlation, like 0.85. I think there's a lot of, there's still something to work here about comparing products with the right resolution, because if we have very high resolution from INSAR, sometimes we can mistake the high resolution for errors when we compare to lower resolution products. Okay, and then regarding synergies, I have listed products that ERP thinks that have a lot in common, or we can have some synergies with this. From my point of view, I think one key question would be how to merge backscatter and phase information, even when they're coming from the same sensor. It's not so easy to discuss this. And then thinking about the future, we have to think about L-band, which is it's a frequency which is not so much available today from SAR, but it will come. NISR is going to launch soon. And then I think L-band has a lot of advantages compared to C-band. We expect much more coherence, which means the phase will be more reliable. This will mean better coverage in space and time. We expect better sensitivity or similar sensitivity to C-band. Things are penetrating, the radar waves are penetrating more into the soil. The phase effect is smaller, but they're penetrating more. So basically, it should be good. And if we think about ALOS-2 and NISR, they should pave the way for Roselle. I've put here. And that's basically it. So yeah, I have a little animation of the weather radar on top of the ESA-based Soil Master product here for Spain. And so thank you.
One short question and one short answer. That was very fast. Thank you very much, Francesco. So then I would like, normally I should invite now Luis Samaniega to present the 4D Hydro project, but he got stuck on an airplane in Frankfurt for 5 hours, I think, yesterday, and had to stay in Frankfurt the night and go back to Leipzig this morning. So Luca Brocca has kindly accepted to do the presentation on his behalf. So please, Luca.
We need the guy who solved the PDF problem.
I didn't. But I think the
screen say something like this.
I think it was a problem was to share.
It's gone. There was a guy before. That guy. Yeah, come, please.
No, where it is. Or you can share the screen.
It's control. Just wait a moment.
It's a PDF.
It's a PDF.
Yeah, yeah.
It's this one.
It's control P, right?
Window.
Window P. Yeah, and
Oh, yeah,
duplicate.
and duplicate. Oh,
Okay.
and then full screen.
Okay. Yes, I'm giving this talk on behalf of Luis. Actually, he also made a mistake in writing my surname. That's fine. And yes, this project is a kind of first approach or from ESA, actually, for involving as best as they can land surface modeling community. And indeed, in this project, there are a lot of really, I don't know, 9 partners probably. There are land surface modeling people who are making high resolution land surface modeling at European and global scale. And the idea is to integrate the Earth observation land surface modeling community as best as we can. The objective of the project are first trying to understand uncertainty in EO-based and land surface modeling data sets. Improve the data at 1 kilometer, so providing also the data at European scale. And then we have 5 science cases that are related to extremes, drought, floods, hydropower potential, water management, and also the classical science case related to the water balance closure. Of course, we are going to provide also tools and to access the data. We have a stack catalog, and we will finish with kind of roadmap for the future. So this is the old paradigm. I don't know how much it is old, but actually, basically, Earth observation should solve the problem of, I don't know, I've never seen like this, but Luis see like this, that Earth observation actually should solve the land surface modeling problem of getting the data. But now actually the new paradigm is basically to integrate the two. So to use Earth observation to improve modeling, to use modeling to improve Earth observation, and so basically to co-develop the two approaches for at the end obtaining essential climate variable for the different component of the water cycle. We have three study regions. One is 4 study regions. One is for Europe. Then we have a basin in southern South Africa, and then the Rhine in Germany and the Po River in Italy. We have collected a lot of data also from in situ stations for river discharge, but also precipitation, soil moisture. And the first product we are now, I think, I'm not completely how much how far we are, but actually we are developing a stack catalog that is available in the website. The website is www.4thehydro.eu. And in that website, there will be the catalog of these data sets that will come not only from Earth observation, but also from modeling. And there will be also scripts, Python and Jupyter Notebook to access the data, a blog for getting the data. One of the things that we are going to make is the round robin experiment, in which we are going to compare different data sets. I think I have slides for that. And then the idea is that actually we have a kind of first tier of land surface modeling simulation. Then we have a kind of round robin to assess the best EO products. Then these products will be used together with land surface modeling, and we have a tier 2 data sets that in principle we should see some improvements. The stack catalog is, the slide of the stack catalog is here. You can access it from the website and also from the link that you can see on the right and on the bottom. And this is kind of sample of EO dataset. So for instance, we have 1, 2, 3, 4, but I guess we have even more. But these are the datasets that we have for ET, Precip, and soil moisture. And in principle, all the data are for the same, so ET is for the same date, Precip is for the same date, soil moisture also, and actually they basically should be, all the maps should be very similar. Probably the best map are for precipitation, but for the other product, actually, this is not really the case. You can see some patterns that are quite different, and so that's why we need to improve. This is a kind of impossible to read the slides for, but it's simply to say that basically we are going to make a very detailed assessment in terms of different performance metrics on the x-axis, different basin on the y-axis, and also different model. So 1, 2, 3, 4, 5, 3. Yeah, we have 7 models running. So we have already 7 models for the whole Europe and for the different basin. Some of them for the whole Europe, most of them for the whole basins. So we make the comparison between EO products and the modeling in the tier 1 version. Basically, the idea is that when we will have tier 2, the performance metric should improve. So basically, the improve means everything close to 1, more or less, should be like this. Yes. The first, this is also, the first round robin for soil moisture was done, probably from colleagues on Tuvia. And the idea of this plot is that if the dots are blue, means that Earth observation is better. If the dots are red, means that ERA5 is better in comparison with in situ data. And so, for instance, we have 5 different products that have been tested. And for instance, the best one is the SMAP 1 kilometer. I don't know which one it is because there are different SMAP 1 kilometer products. But if we have done blue dots, means that sometime somewhere Earth observation data are better, but mostly they are red dots. We have a session, and we are going to invite you to, if you are interested to these kind of things, for the integration of Earth observation and modeling, that it will be open for the next EGU. Recommendation is, yes, co-development is the first point, and to reduce the water balance closure. And ESA should contribute to initiative that contributes to the co-development, and this is fundamental also in the direction of digital twin initiatives. And this consortium, should concentrate on solving the grand challenges in land surface modeling. You know, the land surface modeling community is quite strong. They started already several years ago. There are 2 community papers already published, and basically they started already in 90. And this is a sentence from Eric Wood that he got from a paper on, very long time ago. And so the idea is, the main science problem here is that what should be the resolution of modeling and simulation. So how far we can go, how far in terms of which spatial and temporal resolution makes sense. So it makes sense to run a model at 1 kilometer if we see that basically the results are not so different from the 5 kilometer or 10 kilometer scale. And so that's one of the main science question of the problem of the project. Thank you very much.
Thank you very much, Luca. I think we need then to pass on to the last presentation, which will be done by Karim, presenting some of his work.
Yes, thank you. So I probably have the least fancy title for the project, Storage Discharge Relationship. But I should also say that I'm also the least funded ESA project. So it's fine. Actually, it's not really a project, as Espen said, it's just research I carry out at the Science Hub at the ESA-ESRIN when I have time. So the main idea, so I have a satellite geodesic background. So when I started getting interested in hydrology, the first thing I did, following advices from colleagues, was to plot discharge of rivers as function of terrestrial water storage anomaly derived from grace. So I will show you a few examples here over the Amazon, but of course you can generalize it to all the rivers, providing they have the basin has the appropriate size. And so you can see here in the Amazon like 2 examples. And when you plot this curve, you see that you have approximately 1-to-1 relationship between discharge and storage. It's not, of course, exactly true, but it can be a good approximation. And that will be very interesting because you can have approximately another constitutive law describing the drainage. Of course, it's not always the case, and you see if in this basin already it's hard to make this approximation of a 1-to-1 function between discharge and storage. And if you look at other, then clearly you see that it's definitely not a 1-to-1 function, but rather a hysteresis loop. And it's this on basin of different size, as you can see on the map. So the simplest case is, of course, when you have like a approximately 1-to-1 relationship. And this is really interesting because, to quote, I think a quite famous article, then you can infer a simple dynamic system. So the drainage basin as a simple dynamic system. Why? Is because, of course, if you have a mapping between storage and discharge, so that's a Q discharge as a function of storage S, which can be an analytical formula derived from some theoretical ideas, so like a power law or any non-parametric curve. Then you can combine it with mass conservation. That's the second equation. And eventually you get one single equation, which is actually discharge storage and precipitation, discharge, and storage function. So it's a differential equation, presumably not linear, but that's catch most of the dynamic that you will observe. So that's typically the simplest conceptual representation that you can have is simply a bucket with Q as a function of S. And that's very useful because once you have that, you have a complete model, very simple. And you can do, for instance, forward simulation. So here, that's an example I show. So providing you have precipitation minus evapotranspiration, you can estimate then your discharge and also storage anomaly. By the way, you need to estimate some parameter among which the S0, so like the offset on the storage. So you can also infer the total water storage. So that's an example of what you can do. You can even do, so to quote again this article, do hydrology backward. That is, providing you have the observation of your discharge, you can go back to the input, namely precipitation minus evapotranspiration. That's an example here I show again for this river on Kurikuriari flow gauge. And here I reconstruct P minus E from 1980 and compare it to ERA 5. So no metrics, no error, just to show ideas here. Of course, and that's a most widespread case. That's not new, actually, of course. You don't have a one-to-one function, but you have hysteresis. And it's very interesting to try to identify what is the mechanism of this hysteresis. So it can be a phase shift between storage and discharge, or path-dependent dynamic, or simply different mechanism, or different different variables that are not taken into account. But if you take the example on the so on the left-hand corner on the top, you see clearly when you plot so this discharge function of storage and with the color code the precipitation, you see that you have clearly two mechanisms. One related to the surface flow. So one cycle is basically 1 year. So, okay, so it takes 1 year to cycle. So you have in the ascending curve the surface flow and mostly base flow. So base flow dominated flow when it's decreasing. So this gives insight into the physics that is taking place and give also ideas how to properly model it still with very simple conceptual models. So here I tested two, actually I tested one, but I have ideas for two. The first that I tested is again a one bucket model. So with an implicit modeling of the discharge. So here you will not have a function Q as a function of S, but rather a differential equation where the derivative of the discharge is a function of parameters, namely S, so the total storage, but presumably also of precipitation, and you can add some moisture. And the big issue, of course, is to identify this function. And to have a maximum flexibility, of course, the idea that is also very fancy is to use a neural network to model this function. The second that is still an ongoing work is really to have once you have identified these two dynamic processes, is to try to catch them again in a conceptual model. So basically here was two buckets model, one giving the surface flow and the other the base flow. And again, using the flexibility of neural networks to encode the flow functions. And of course, this framework ensures that you have mass conservation. And you can also then separate the different processes and characterize them. The tricky thing here is more mathematical. Is basically you have a set of differential equations, and inside the set of differential equations, some neural network that you need to calibrate. So it looks like super fancy, and I was very happy to have this idea. But of course, you just need to Google it to see that many people have thought about it way before you, and even have found solutions how to do that. But okay, once it's done, so basically I've carried on this example for the implicit modeling of Q. You can again have the same model, so precipitation, storage, discharge model, and do exactly the same thing as before. So for instance, a numerical integration to carry out the forward simulation. So simulating flow and also total water storage from any time in the past, providing you have the input. Okay, try to go quickly. So the objective here overall is not high resolution in terms of spice, is rather to infer simple and physically informed reinforced storage discharge model using data from GRESS to inform on the dynamic that is taking place. And once I have ideally identified this flow functions, try to relate them to theoretical model, for instance, Boussinesq equation for groundwater flow, and to a geomorphological parameter of the catchment. And that's it. Yeah.
Questions or comments to this? Yes, Peter.
Yeah, thanks for the interesting presentation. I've heard nothing about uncertainties and errors and biases. So how do you plan to deal with that? Because I think, and I missed that in quite a few presentations, is understanding where the uncertainties come from. And I think that's a very important thing. We can all show and come up with different types of models to match our observations with what they want to, but it's understanding, of course, what our uncertainties are. That's the big deal these days.
Yeah, I think the advantage of this kind of simple, also I would say even heuristic model is that you are able to track, not analytically, but you will be able to track the uncertainty. So here, for instance, for the forward simulation, if you add the uncertainty on your input, then you will be able to propagate. So that's probably some good math, typically Monte Carlo. I mean, if you have really nonlinear function differential equation. So I've seen it done with Monte Carlo. You simulate many times and you have an idea of the uncertainty. Maybe the better okay.
Just adding a stochastic function to that. But that's not understanding uncertainty. You have to understand where it comes from. And a clear example would be how well do you understand infloration physics related to it? And don't think we do. It's coming up with some stochastic function on top of it. Doesn't explain the uncertainty. It just turns into a nice little more random process.
Right. Yeah.
It's not a random process. It's a physically different process with uncertainties. Because we don't exactly observe the parameter. Make errors in the instrumentation, errors in our models, working response to our radiances to whatever. So that's what I'm getting at. Is that don't get it wrong.
No. But I'm interested, but I'm also a bit puzzled. That's a big question. No worries. Of course, what my answer was then a bit different because it was more about uncertainty propagation right? So basically, again, this one you can also do it. I'll not show it here, but if you have also your uncertainty on your observation and your input, you can use typically CAM and filter or this to propagate it nicely. But I get your point, and yes, that's not something I will be able to answer. But maybe already, I mean, I don't know if we can start discussion right now.
Yeah, I just do like to comment
point.
that this is a typical thing that you said, as you said, it's something which is common between many projects, and it's a typical kind of cross issue that we could discuss in when we meet. I mean, when we're meetings of the cluster. Now, okay. For example, last week we had a workshop together with the Commission in ESRIN, where we had meetings of the different inside the event. We had 6 different parallel workshops on science clusters. So we had almost 2 days for each cluster to discuss cross things. Now today we have 2 hours, so it's not like we can do much today, but this could be a typical thing to have as a discussion topic, have some introduction with presentation and have this long discussion on such issues. That's typical what we could do as part of the cluster activities. But as I said, of course, don't have the time today. But what I wanted to do today, seeing what remains as time for us, was to have, we wanted to show one potential idea for what could be done in the future. And
yeah, that wasn't the case where absolutely no contribution would come. So yeah, so I have prepared just 2 slides, just really like just sit question to provoke a bit of discussion. But basically, that's who I think should be of interest for you if you want a new future project with ESA, then and choose the topic, choose the orientation, which direction we should go. Yeah, there are many things that could have to be addressed. So, for instance, better hydroclimatic variable estimation, if you think it's required, better hydrological process understanding, if also you think this is something that is still missing. Also, the problem of addressing small catchment. I mean, I've seen in many presentations, big catchment, sometimes just a few around the world, which is more than fine. But indeed, if you consider floods, which is a topic of very important for Jérôme, it's mostly happen on very small catchments, and this needs to be addressed. And if you're considering small catchments, then you have to consider there are many of them. So you have also to consider this so-called large sample hydrology, so addressing hundreds, if not thousands of catchment. And you see more and more database that gather all the data to do this kind of studies. Another topic that's I throw here is also water quality. That's something that's not addressed. I don't know if this can be a topic relevant for Earth observation. Yeah, that's ideas, topics that could be relevant for next ITTs, for instance.
Thank you, Karim. Any reaction to that? You agree that this could be priority for new activities?
The one in gray is really, if you have no input here, I will give mine, and mine is I mean, really for writing the next proposal for an ITT will be to consider the monitoring and quantification of groundwater dynamic. So as I say, I recall that it's hard to say because it's not well quantified, but it's approximately 30% of available fresh water, and you don't have so many. There are, of course, but you don't have so many studies on this at local or global scale. While I think it has been a bit touched by some topics. For instance, irrigation, I think, can be related also to this topic of groundwater. I don't need to say how, I mean, important it can be in some region to properly monitor this. And so the question that I had for if this has to become a proposal is satellite EO the best data to address this topic? And that's where I would need your input here.
Please, Christian.
I just comment on this. We should try to having them to sense that there is already a large sense seeding paper is the one problems here. As community, to understand that we could solve those it's a good starting point.
Thank you, Christian. Any other comments? Luca? Yeah.
So, namely, take a clear example like discharge estimation. Should we like come to, I mean, gathering all the methods, gathering all the data, and making at the end a full comparison? Is that what you mean?
Yeah. My impression is that actually we should really go for projects including not only one of the science is not the and the experience that we had with this kind of it's not discipline, it's actually the integration of multiple people together, and it works very nicely. And it works nicely also to include the modeling community. And probably here we can address the 20 and solve the problem with them. And part of that paper is correct on them, but and there's something to be done, and integration between the different places of the quality of flow, perhaps what the AI for EO for water transfer, and then there should be kind of strong transparency between the departments. For example, we are working on the presentation for 3 or 4 different projects. The same, so that's something that we should do. It's actually, it cannot be a project to make, but the cluster probably is the function purpose of the cluster.
Yeah.
Make
Yeah.
these kind of teams here, and all the people are aware. And also, in order to make, for instance, projects, there are many people for the permanent forming, which definitely acquire the projects.
Sure.
And so to be there, kind of quite established.
Okay, thank you, Luca.
I wanted also to add another point, but Philippe has make the case even before me, which is in many of the current or previous ESA projects, of course, there are very good scientific cases, but not a lot of artificial intelligence, machine learning, for hydrological modeling. I'm not advocating it. I'm a bit also skeptical, but it's a fact that if you read the literature, you will see that this LSTM long short-term memory neural network gives really very good performance in prediction. The usual critics that is given is that you lack you totally lack interpretability when you're doing that. So you're simulating or you're predicting very well, but you don't know why. Of course, it's not as binary as that. Of course, you can find some interpretability. Enforce your neural network with physical laws. But I think it will be interesting also to put more effort, more endeavor in integrating machine learning in the next ITTs.
Yes, Luca.
That's a perfect example because there are the German guys we met last week. So they are working on this direction.
Yeah.
We have done a lot. They are the big guys, Einstein, Marcus Einstein, and Jacob with the signing. They are working a lot on this. I was not aware.
Yeah.
Mhm.
So
okay, no, that's a goal over our cluster. Is main goal to try to share this information better. Yeah. So before just 2 minutes before we close the meeting, of course we don't have the time to discuss about this, but the question was more: is this, for example, a subject that we should discuss during a next meeting of the cluster? If we organize a meeting with 1 to 2 days, where we can discuss some cross topics, cross thematic. Is this a thematic, an issue that we should, you're interested in discussing? Yes, Diego.
Hybrid way that makes sense before it starts replacing the physics that we have been learning. So I think we have to be proactive. I think that there is no way around but to actually ingest it.
Okay, Christian. Sorry,
next one.
Okay.
So I won't put the use of machine learning and artificial intelligence only on modeling and forecasting. I mean, machine learning, I think, is important also for hypothesis testing in hydrology, data augmentation. I would put in a more broader sense this.
Okay, thank you.
I would say that's also this machine learning can also enlighten also physical process understanding and maybe try also to unravel it.
I think that we as a hydrology community are very far away from the state art of artificial intelligence algorithm. We talk about always Elystian, which is an algorithm that used 2018. But now we have many algorithms that are never tested in our application. This is my first comment. And the second one is that these approaches, the hybrid model, is really important for the engaged basin, which are very important in the hydrology. And I think that this is one of the priority of the ESA for the next step that focus on the engaged basin. We are always talk about the product, the product that is more important for, I don't know, for the application, but we just focus on the area that is not, that is have a density gauge basin. So yeah.
Okay, thank you very much, Peter.
Yeah, we have a tendency to look at ungaged basins because we sort of seem like they're not properly observed. I think we actually have a much bigger problem with our control basins because there's so much human interference that it's actually much harder to do the forecasting. in these basins than it actually is in many of the ungauged ones. A, because they're a lot of times smaller, but B, because they're actually not as interfered with as many of our controlled basins. And I think one of the aspects that I sort of was lacking is indeed irrigation is a big part, but you know, all the controls that we have on our basins in many different ways is another aspect that I think would be deserving of a little bit more attention. Well, for instance, you know, flood control. So it's not just flood forecasting, but flood control. The different ways we do that, the different ways the farmers control the amount of water that they take out and put in, the different ways industry plays with that. And there's so many examples that you can come up with. And it's land cover change is also a very big one. We tend to see things a little bit more too static. And I think that's a challenge that we have to deal with, is how do we, particularly when you go from prediction to projection, is how do we deal with that part? So really going away from the weather to more the climate timescales. Yeah, how do we, you know, use Earth observation in our modeling and really put a lot of added value in there?
Okay, thank you, Peter.
Comment, actually, all models basically consider land use and land cover as static variable. And they don't change. Land use and land cover typically is considered a static variable. It doesn't change. Now we have data also dynamic in time also.
Yeah. True. Okay, I think we need to close. I'll just so that you can get some coffee. Just like to say a couple of words about the next steps. So we will create a website for this cluster. We will include the presentations of today if all the speakers agree. Then we will also share some information about EC projects. So Panos Balabanis, he didn't make it to come today. He will come later this week, so maybe we'll get some. At least he will end an intervention on the Friday, but it's a closing session, so I don't know how much detailed information he can provide. But at least we will share some information, and then the goal is that we have a meeting later where we meet together with some of the EC projects, and we can discuss issues like we have discussed today with artificial intelligence, uncertainty, other issues, and also more about what is future priorities. So I don't know. When we haven't planned for when this next meeting should be. I don't know if there are any other. We could either try to link it to an event like we did today, but not an event that lasts for 1 week, so that we don't have any time. But other events, if somebody knows about some event in the next, let's say 3 to 9 months, that we could link such a, for example, 1.5 days meeting too, then I would be very glad to hear it, a meeting where many of you plan to go. And if not, we can try to organize a meeting for example, in ESRIN. So that's the kind of the next steps. So yeah, and I think I will just let you go to coffee instead of trying to get information about what are the best events. So thanks a lot everybody for your contribution, and looking forward to work with you also in the future on this cluster. Thanks a lot.
It's okay. Good afternoon. Welcome back. Welcome to this first session, Advances in Science and Process Understanding. So we will have 5 presentations, 20 minutes for each of them. So I hope enough time, and also enough time, I hope, to have a few questions. So we'll try to keep it sharp, and have also 20 minutes at the end for to further discuss some questions that we prepared, or whatever suggestion you may have. We start. So first presentation by Luciana Fenoglio, that I invite to join. Stage is yours for 20 minutes. I
Thank
will
you.
give you a hint after 15 minutes.
Thank you very much. So welcome to my presentation this afternoon. So my presentation is about discharge and water storage change from modern air satellite altimetry. I would like to acknowledge my colleague from CNES and from CNR in Italy and from OSRS. So I would like to, yeah. So it's not continuing. It's not going on. It's there.
C'était pas mon présentation,
It is.
Central. But why is not working then?
Why it does not work with the WebEx? Can you close this?
Doesn't go.
Do not show this message again.
But the pointer is not working, you know?
No, but that's not a problem.
Or maybe if we can try to move the slides with the computer.
Shows. Shows. Can we then simply duplicate?
No, duplicate is
Why?
So
Yes.
Daniel, next one.
Yeah, but we have to keep it
Zoom.
Zoom WebEx.
because they're
WebEx.
good, isn't it? And they're
No. So
not sure if you share the screen. All right. Then let us try to move. All right, it's okay. It's okay.
Once again.
Wait.
Say this.
This no. Okay, it was not. Oh. All right, it's okay.
Okay. So I have my 50 minutes. So to go,
still have 20 minutes.
so can you try again here? So I'm going to the next one. I'm going to the next one. It doesn't work. Can you come here 2 seconds? So I'm pushing here, correct? we try before they start. Yeah? Then we can start to count. I can use this way, right?
Yes.
Yeah, let's use this way.
It's changing. Yes.
Yes.
So maybe
Since I
yeah.
use the other way, okay. Just try, yeah? Small try. Works? Perfect, we love. So thank you very much for being here. So I would like to start my presentation now with a short overview, and then I will have a scientific question, methodology, and my result. So what are we trying to do in this presentation? So I would like to show what we, at the moment, we are doing with the altimeter data and what we would like to do, and also to understand which is the best way to do this. It's and what we are aiming to look at the water cycle and surface water we have, looking at this interesting theme, we have some challenges. The challenges are, first of all, in the observation, because the in situ data are decreasing, as we all know, because we have also other information, for example, from the human influence that are not very well given in our in situ data. We have also challenging modeling. So we want to have good modeling, but the good modeling need very good high resolution data in time and space. Do we have this from space data? This is will be my what I try to reply, and will we have? So, and then we also have a need to work IPC, because we have processing which are quite high demanding, and so on. And at the end, we would like to work in our world. So here, this my project, for example, is founded by a collaborative research center, 1502 from German National Council, and we are trying to solve this question. And my work in this project is to work in a sub-project which works especially with altimeter data. So this for the overview. Now, the scientific question is what I explained already. So we are interested in climate change and to see if with the climate change, will the river discharge change, and not only the river discharge, but the amount of water on the Earth. And another important question is if we can separate natural availability from the human water use. But first of all, we have to know what we observe. And therefore, for me, the really scientific question is how to use at best the space data that we have and that we plan to have. And for doing this in our project, we are looking especially, we start to look to this part of the world, which is Germany, where we have good data, and that therefore we are able really to validate what we observe. This is a quite busy picture, but the only things that you have to remember is that we decided to start from the best, from the top of the data. This means from L1 data that in altimeter data we have, and we proceed until level 3 or level 4. The parameter that we are looking at is water surface elevation, is discharge, and this water storage. And then we want to construct a regional database, the first for Germany and then for Europe, and in this project. So we look at the old database. So what do we have in the old database? This is the first question. So we have the river discharge for the GRDC. In Germany, we have the luck to have data until a few years ago. And what we look at this, and we have a quite long sequence of data, and we see, for example, that there is some change. There is changes, for example, in the maximum of the height of the water in the river, and this is in the River Rhine, and this is, for example, here in Worms. So we have a displacement of the maximum of the height in the beginning of the year, so February or March. Before it was in May. Also, the cycle is not anymore very seasonal, so it's quite chaotic. And also, we say, okay, we can use altimeter data. Do we have good altimeter data to use there? And we use, of course, the data from TEIA and from the ET database. However, these databases are not available at all of our virtual gauges in our region. And so this is also to be expected because they wanted to have data all over the world and not only in our section. Therefore, we decided to process ourselves our data. So in order to do that, we started to have a look to the data. And we see, for example, that in some region, these are time series that we have, we can have very good accuracy. The question is how accurate are the data that we have? This, for example, is the station of Mainz. So we have an accuracy of 9 centimeters with Sentinel-3 and Sentinel-6. So this means this is what we can have. But we don't have only one virtual gauge. We have 42 in Germany. What happens if we look at all 42? If we look with the old, so with the available data, 20 Hz data, which is quite, 20 Hz is quite low in order to look in a river. We look also with different ray tracker, and then we compare with 8 years from Earth console. And we decide, okay, we have 20, in this case, we have about 20, 25 in median and 40 in mean. So this means that we prefer to use ATS data. Then we tried to look now at the dedicated processing data. So we had a project called Hydrocoastal where we did all this analysis regionally, and we find really good beta data, bad result, respect to the original data that are available, the statistic data. And we have, in principle, about 20 centimeter again, like in Samosa Plus. So also with the data of DTU and processed it in L2, L3. So this means that with dedicated processing data, we get again the 20 centimeter that in mean for 42 gauges that we want. Then we decided to go further on to look at fully focused data. So fully focused data is a very interesting processing because especially in rivers, you can have a very high resolution along your track, and then we consider, for example, here Sentinel-3 is a unique situation where we have a 30 kilometer of Rhine under Sentinel-3 in our region. There are not a lot of regions in the world that we have this, and you see also here. So we continued today make this analysis and comparing different frequency of processing at different frequencies, but concentrating the ATS that we have seen before, we arrive at 15 centimeter. And we realize also that processing the data also in unfocused SAR and fully focused SAR doesn't change too much. The important is to have ATS. So my requirement would be to have now suggestion to would have been to have so this ATS data everywhere. But when we look, for example, at the data, so it's a small tracks here, we see the difference between if we process in 20 Hz or in 80 Hz. So of course, 80 Hz is a little bit busy, a little bit noisy, but it's clear because it's not averaged. And you see also here in the diagram that is quite more easy to see. So the fully focused SAR is my choice at the moment, and I continue with this. I continue to process in fully focused SAR at 80 Hz. Here you see a processing that we are doing ourselves, and this is processing from NOAA, also at 80 Hz. And then also unfocused SAR, again at 80 Hz, and so on. And the question here, how are they different one from the other? Do they differ a lot? They do only differ in resolution, or they differ? And then I invite you to look at this poster. There is a poster from Vigneault Daly et al., which use the PISA individual echoes. So is a difference using the PISA individual echoes or using a fully focused SAR where you have a very high choosing a high frequency? That you can see at the poster, but I can also show here why, if yes or not. There are two differences. So first of all, I have no difference when I compare with gauge here because I have 20 centimeter using fully focused SAR processing by us and the individual echo from PISA. So again, 20 centimeter we have. But if you look at the radiogram, we see quite easier things here. For example, we see that in PISA, we see that there is this part here, which is you don't see what it is, but it's I saw it. Is here, yeah, this here is a pond that is nearby the Rhine. Is this one? So this means that in individual echo, you are working with individual echo, you have quite better capacity to find this. So then fully focused SAR, it seems that it doesn't bring too much to the precision or to accuracy of our data, but it brings more on data resolution. So this is the part where, so if now we have our fully focused data, we are processing in water height. Now we have to compute the discharge. And to compute the discharge, I use a simple formula, this simple formula for Berkeley, that is given like this, where you have the coefficient which are already fixed, and this one will be estimated, or perhaps you can use the values that Berkeley found using 500 years in 500 gorges or rivers in the United States. It would be strange to think that the values that Berkeley give us works also for the Rhine. But you are wrong if you think that is not possible, because they work perfectly for the gorge of Worms. In Worms, when I use this coefficient, or if I compute myself in a least square this coefficient, I get 8.7 and the other is 7.41. So it's very near. And you see also from here that the curves are very similar, computed with different methods, assuming this as a synthesis of these formulas or to evaluating the coefficient. So my conclusion is that this formula has to be calibrated in our region, and we also did using different reaches. But the question is also, is the slope, this formula can be completely computed by satellite altimetry. So the slope S here is computed as the difference in height divided by the length of the river between the 2 points from satellite altimetry into virtual gauges of the same track. The question is also, is slope changing in time? So we have heard yesterday that there are some good reason to think that the slope is static. But for our case, we analyze this. The slope S is changing in time. In the Rhine, is changing between 8 centimeter and 11 centimeter. And therefore, when you put this formula in your formula to compute the discharge, you expect to find some different result. At least it is not correct to consider. Yeah. And then we computed, this is just to show that you just simply computed use the slope computed from altimetry, the river depth that you can compute from altimetry, also in this case we took from a model, but it also work, and the amplitude that you can compute from different, the width that you can compute from different way, and we find this solution. So we are happy that we can apply the formula of Berkeley with attention that the slope must change in time. And here, just to show, I don't want to go in detail, but yesterday was also discussed how the slope change. And if we have a higher regime, we have a lower standard deviation of the slope. And the slope change in time, here the standard deviation along the time, and so on. And this was done with the simulation from the Sobeck model that is used for the Rhine. So now, I go now to the future. So this was until now the satellite altimetry that we are using. We decided that we will use fully focused SAR, and now we are going to the first. I would like to show you some results that we got with the SWOT data. So I am in the science team, so I have the chance to get a view of this data recently. And you see here, this is the station. I have 3 stations here. So I have the station of Worms, which is the first one. And then I have the station of Koblenz, of Mannheim, and this is the station of Koblenz. And what I did, it was to compute the standard deviation between the SWOT data and the vortex station. We have 3 vortex stations in bridges, and we have computed this. And we find, in the first case, we have 22 centimeter in Worms, we have 31 in Mannheim, and we have 38 in Koblenz. It's quite a high value for someone working near altimetry that we have 9 centimeter with Sentinel-3. But we are confident because in the data that the new processing of the data that have been done from CNES and JPL recently, but are not yet available, with the same in the same region, with the same data for the vortex data, but with different input data from SWOT, we get 7.4. So the pixel cloud product in our region will work good, and we will get easily similar result to what we have with altimetry. Now, the last thing that I want to show you is what we did ourselves with the other product of SWOT, the nodes and reaches. This is the node. We have data every 200 meters in the node on SWOT, and you get the water surface elevation and the amplitude. This is a reach near Bingen, so it's in Bingen here. And I compared with the tide gauge in Bingen. And I get 8 centimeter. So the data of the nodes in this region are very good. And you see that you remember that I wanted to compute the discharge using height and width and then multiply by the slope. And then this I will do. I have not yet done, but we will do because we have 8 centimeters standard deviation. Another point is not everywhere the same. Here, for example, we have here again sign. We have also GNSS reflectometry there. I have no time to show this, but I show the comparison with a gauge, which is nearby, near to one of the 200 meter point, and we have 13 centimeter standard deviation. The last that I want to show is in Mannheim. So you remember that we have looked that we have 30 centimeter with the pixel cloud. Here in this case, we have 14 centimeter or 21 centimeter. Mannheim is quite a busy region because we have the NECA that is coming here, and then it would probably explain this part here because it's before. So it could be a good hydrologist could tell me perhaps the water has come back. I don't know, but this is what I could imagine because it's very nice until when it's match the NECA and then it starts to have a problem. So we have 21 centimeter. So to conclude, I wanted just also to say that we look at the lake. And the lake, we had using fully focused SAR, we could look at Lungener See in Switzerland, which has an area of 1 kilometer square. And we were able here to compute the hypsometric curve, very good data from fully focused and so on. We don't have in situ data to compare. We'll try to have. We could compare SWOT in the lake of Constance, the lake of Geneva, where we compared SWOT also together with Sentinel-6 and Sentinel-3, and with SWOT compared, validated with the gauge, and we had here in this case 2 centimeter of standard deviation and the other 5. So with this, I would go on to my conclusion. So the conclusion, so in principle, in our study, we wanted to have a close look to a region that we know very well. So we know what happens there, and therefore we could also have some information about the status of the altimeter data. So we have, indeed, it's interesting to work with this data for climate change because we see some changes. The data in nadir altimetry is a very nice thing that we had for the past 30 years. They are increasing in accuracy and so on. With dedicated processing in fully focused SAR, we can reach the limit that they have. And probably there is not much more to do on that. We could derive the discharge using this data just using a long-term altimetry, and the same for the storage. But now that we have SWOT data, I think that we will have to think completely in a different way because we can use this data in so much more easier, of course, when the work or the calibration validation is finished and we understand them completely. So thank you for your attention, and of course we want to mix the both.
Thank you, Luciana. And we apologize again for the technical problem at the beginning. We have time just for one question or one comment, if any. If not, then we move on. Thanks again. Our next speaker will be John Rieger from GPL. John, please. Here we close this one. Super. Oh, tell me it's working.
Yeah, it's good. Great.
Yeah.
Yeah. Okay. Hello, can you hear me? I'm JT Rager from NASA JPL, Pasadena, California, and I was going to give a talk on water cycle events in the global mass budget. And since I've been here since yesterday, I thought that maybe that was not that interesting of a project to talk about. And so I've decided to actually cancel this talk and do a different talk, which is called the Big Mount California Groundwater Recharge After a Record-Breaking Winter. So I'm really lucky to be able to work on multiple projects. This one I think is more relevant because it's a bit of a survey of different remote sensing techniques applied to a single problem, an event-based problem in California, and it's going to end up really articulating the strengths of satellite gravity. So that's kind of my goal ahead of time. You know, I think it's nice for us to be here from JPL, from NASA, and we've got a small contingent here and be able to understand what's happening on this side of the Atlantic with the remote sensing and hydrology, and then also to be able to offer something in terms of the research we're currently working. So this is what I'm going to do. So to start with, we had a really extremely wet winter in California last winter. This is the snowpack as of April 1st. As of April 1st. Let's see if I can find as of April 1st, 2022 versus April 1st, 2023, a lot more snow in this year. And this is a joint project that was sponsored by some internal JPL funding to actually understand this big wet winter and what are the consequences of that water. So that's what I'll talk about. It's mandatory at NASA that we put a NASA symbol on our slides. And so I put one up here with CNES, GUX, and ESA. And I started with one, but then it didn't quite look symmetrical. So I put two in here in the gaps. So it looks like NASA's taking over, but it's just because I had to put something on the slides. So bear with me. So how much precipitation did we have? So that year in California, 2023, we had 9 atmospheric rivers from December 26th through January 17th. So in a 4-week period, we had 9 atmospheric river events, 9 storm events that came into the state. Over that 3-week period alone, 32 trillion gallons of water fell in the state. In a normal year in California, we have maybe 4 or 5 atmospheric river events, and those bring pretty much all of our precipitation for the year. And if we have maybe 3 or 4, then it's a dry year, we're in drought. If we have maybe 5 or 6, it's a really wet year and we're flooded. This year we had 9 atmospheric rivers in a 3-week period and a total of 19 atmospheric rivers over the entire winter. So off the charts, the amount of precipitation that we had. And this is the path of some of those atmospheric rivers. Those storms come off of the Pacific, and just when they hit the mountains here in California, they just drop tons of snow and rain. So it's really wet. So we have a snow scientist at JPL named Noah Mullich, and he's actually in the other room right now giving a talk about these plots. So if this is something you're more interested in snow, you can still have time maybe to run over there and catch that. But it's pretty much this. Actually, mine's more exciting. I think you should stay here. So, but Noah invented this term, snowpocalypse, for how much snow we had last year. This was, again, April 1st, 2023, snow water equivalent in inches versus the average from 2000 to 2021. So much, much wetter. Some ski resorts that we have in California received as much as 58 feet of snowfall over the winter. Roads and towns throughout the state were inaccessible, and we had about 300% of our April 1st average in the southern Sierra Nevada mountains. So Noah did a story with the Los Angeles Times, and he told them that we got about 50 cubic kilometers of snow water equivalent in these mountains, and that if we melted all that snow, it would cover the entire state of California with 5 inches of water. When he said that, the LA Times put that in an article and published it. And people from throughout California started calling the LA Times because they were scared that their home was going to flood with 5 inches of water. So they didn't understand this translation. But it's a lot of water, 5 inches over the entire state. The major questions then, when we have that much rain and precipitation, are how much will run off, form surface water and recharge reservoirs, or how much will flood the Central Valley, and then how much would actually repenetrate into groundwater storage. We have a big groundwater aquifer here in the Central Valley, called the Central Valley Aquifer, and it supports a lot of the agricultural production we do for the state. So surface water formation was the first thing we looked at. And this is a movie of Landsat and also Sentinel-1 images. I think they're switched Landsat and Sentinel-1 images of the formation of a new lake in Southern California. So this is a lake called Tulare Lake that existed thousands of years ago. And then at some point in the 1800s, it was pumped out to make more farmland in California. We had so much rain and snow that this old ancient lake formed again. And it's so big, it became pretty much the same size as the biggest lake in California, which is Lake Tahoe. It was about the same surface area. We had some people that drove out and actually saw this thing from the banks and noted the size. Homes and farms were flooded throughout Southern California, throughout the Southern Valley. And these are the reservoirs in California. They were dry as of September 2021. And then after these storm events, they really filled up to the maximum. So tons of new surface water. And now we have, California is a very liberal state in the United States. So now we have people protesting that this flooded farmland should be preserved as a site of natural heritage, that there's going to be birds landing on this lake, and that we need to protect it environmentally and preserve this lake forever. In the meantime, the farmers that own that land want the water to be pumped off because they want their farmland back. So we've already got a controversy. This is a bit about California. So in California, we have a huge agricultural industry. We have about $20 billion a year of agricultural production in the Central Valley. We grow about a quarter of the produce for the entire United States in California. And the reason we can do that is because it's warm year round. We have good weather. The only limitation there is the amount of water we have. It doesn't rain that much. So to supplement natural water supplies and keep the agricultural production really high, we use groundwater. And this area was charged with natural groundwater during the last glacial maximum. 20,000 years ago, glaciers from these mountains melted and filled up this giant bucket of water. And we use that water up now like it's going out of style. And it's probably all going to be gone in about 50 or 60 years, to be honest. And then we're going to have a major catastrophe, but I'm not allowed to talk about that. Okay. So groundwater recharge is challenging to observe, as some of you may know. Consider myself a bit of a remote sensing groundwater expert, but groundwater modelers also know that recharge is a tough thing. There's a lot of factors that contribute to recharge. So it's how much water you have, but also how much that water can actually infiltrate through the soil and make it into the aquifer. If you have really deep aquifers or complex geology in aquifers, sometimes there's rock layers or other barriers, it really prevents the water from seeping into the ground. And that's the story in California. It's really complex geology and really tough to understand exactly the pathways for recharge and how much water makes it in at any one time. A big controversy kind of in Central Valley is whether the majority of the recharge comes from the top down, percolating through soils, or whether it comes laterally through snowmelt from the mountains and pushes in this way. And you can see both of these pathways are kind of represented in this figure. So we have the best tool that was ever invented to measure anything water related from space. It's called GRACE and GRACE Follow-On. And GRACE does observations of terrestrial water storage changes. Here's shown some time series of California, kind of the long-term trend in decline that we see over the years. We had a big drought from about 2012 and 2013. You see things get red and time series go down. And then we had some wet periods around 2017. And finally, ending with this current year, 2023, we saw this huge delta at the end of wetness. This is the biggest 3-month delta that we've ever seen in GRACE data over the full record in California. So a huge gain in terrestrial water storage. This is only through March. It actually keeps going up a little bit. This is an old movie. We had this produced as the snow was happening. So through March, but a lot of gain in terrestrial water storage. To calculate groundwater from GRACE, the standard practice, things that have been published before, for example, Familietti et al. 2011, is to try to use estimates of what the other variables are in terrestrial water storage and to separate those out to result in a groundwater residual. So terrestrial water storage from gravity is observed if we have an estimate of snow water equivalent, surface water storage volume, and soil moisture. and we remove those from total water storage, then we get this groundwater storage time series. And with that groundwater storage time series, we can say something about the aquifer, how the aquifer water is declining, and even what kind of actions lead to those changes, that variability in terrestrial water storage. So these are the data sources that we use to do that here in California. And just looking at the average annual cycle, the average climatology for all of those data sets, we see something really interesting. We see that the total water storage has a peak like this, but that the time of the peaks of the subcomponents is really divided, really separated in time, the other peaks. So we see that the soil moisture peaks, it's pretty much correlated with total water storage, terrestrial water storage. And that's the biggest source of variability in terrestrial water storage, even in California. It's the biggest source of change that we see from month to month in the gravity data. That the snow water equivalent is also big and comes earlier in the season. And then as that tends to melt, starting in April, May, April's kind of peak snow water equivalent on average, then that comes down. But as that comes down, it begins to fill the reservoirs that are at the base of the mountains in the Sierra Nevada, and it also begins to recharge groundwater. So the reservoir peak and the groundwater peak are later in the year. That's what we would expect from, kind of the hydrology textbooks. The groundwater is kind of this low-pass filtered process for precipitation, runoff, soil moisture, and stream flow, because the water takes time to percolate down. So changes take time to percolate. And then when we look at interannual variability in terrestrial water storage in this region, it's almost all groundwater. The things like soil moisture, surface water, they change seasonally a lot, but over the long term, a lot of that long-term decline and that interannual variability is really represented by groundwater. So two different pictures of the seasonal versus the interannual. So this is the actual groundwater time series estimated as shown before and shown against terrestrial water storage here. We see that huge increase that we had in terrestrial water storage, this is about through June of 2023, is really not present. That a lot of that is accounted for in the soil moisture, in the surface water, and in the snow time series. And that's interesting because groundwater is only rising about 40% as much as terrestrial water storage in 2023. So we're not getting a huge burst in groundwater recharge that we would hope. Terrestrial water storage increased about 50 centimeters, and the groundwater increase was about 20 centimeters in equivalent water height. If we take the derivative of those time series, then we can estimate a change in time of terrestrial water storage and a change in time of groundwater, otherwise known as net groundwater recharge. And that's something important. It's been highlighted in previous decadal surveys, as I mentioned before, but really tough to measure. And so doing this over the aquifer, we get this d groundwater dt time series. And we can see that a positive change in groundwater represents recharge, a negative change in groundwater represents depletion. And if I look at the let's see, maximum rate of change in total water storage, about 26 centimeters per month. And that, as I explained, the highest deltas we've seen in GRACE data. And then the max rate in groundwater recharge of about 16 centimeters per month. Positive groundwater DT, typically about 50% of the positive delta storage. And but it's a little bit more this year. And then this is the distribution there where we're seeing the D by delta T in centimeters per month. Over the story where this would be positive would be recharge event and negative would be depletion event. So we're kind of doing this for the first time with GRACE. It's never been done before. 2023 DSDT max is about 5 standard deviations away from the mean. It's way out there on the end. But the 2023 recharge in groundwater is only about 4 standard deviations away from the mean. So this kind of indicates that that full variability in terrestrial water storage that we saw was not able to be captured in groundwater. We can look at INSAR data as well to try to do surface water, to try to look at surface displacement to understand areas of potential groundwater recharge through the valley. We did a paper previously, this was in 2022, where we combined Sentinel-1 and GRACE data to actually measure which portions of the aquifer are getting recharged according to the GRACE increase in storage and then changes in the surface level measured from Sentinel-1. And using that and knowing a little bit about the geology of the aquifer, we can actually tell whether or not the increases in mass change we see from gravity are going into the confined portions of the aquifer or in the unconfined portions of the aquifer. So see this paper if you want more on that. This was from a previous year. When we look at the INSAR data for this year, this is 2023 versus the same time last year, that steady depletion that we've been seeing for years and years due to ongoing droughts in California. This was a typical pattern of land surface subsidence, of sinking. In this year, we actually began to see land surface rise. And so these yellows are all increases in the land surface that's actually filling the soils, and the elastic deformation happening in that soil is causing the land surface to rise. And we're able to see that with Sentinel-1 INSAR. Almost done, yeah. Okay, so just to say at the end, we've validated these results with well data from throughout the Central Valley. A lot of these wells do show increases, you'll see throughout the valley. Anything you're seeing here that's green is an increase in terrestrial water storage, according to well data, increase in groundwater storage. But these orange areas in here are still decreases. So even in this record wetting event and record recharge potential event, we still have farmers in the valley that are pumping more water than is coming into the aquifer. So the end is not in sight for these depletion events. I was just going to say how underrepresented well data is in the valley, but I'll end here. All in all, a total of 202 cubic kilometers of precipitation, but only about 44% of that, or 89 cubic kilometers, made it into terrestrial water storage, and only about 18%, or 37 cubic kilometers, actually entered groundwater so far. We might get later a recharge happening. This data is only through kind of midsummer, so as I showed earlier, there's a bit of a delay in groundwater recharge sometimes. We had a new record maximum recharge rate for over the GRACE record, at least, of 16 centimeters per month in January 2023. That's 60% of a new record maximum DSTT. The relative groundwater infiltration rate of 60% and groundwater storage gain of 40% may indicate recharge limitations within the basin. And so that's kind of agrees with the hypothesis I mentioned earlier that we don't know if a lot of that recharge is actually coming in through the surface or coming in laterally. And it may be that some of the recharge comes in laterally from the mountains, and that might be the preferred recharge pathway according to these results. So a continued comparison with wells is going to be important through the dry season, but I just want to highlight the fact that the GRACE and GRACE follow-on provide a potentially viable method to estimate large-scale variable recharge rates and sources for major aquifers. The outlook and recommendations, so I just want to touch on this stuff really, really quickly because we were asked to, that we did a mass change, which is a future gravity mission after GRACE follow-on, mass change community assessment report, where we tried to estimate what are the resolutions, latencies, and accuracies that potential end users would want on a future gravity mission. And so those results are presented here. I'm happy to talk about this more offline if people want. But really, that there's a big demand across the board for higher resolution in gravity data. And if you've used any gravity data before, you know that's the major limitation is it's just coarse data. That's just how gravity from space works. But if we map out kind of processes like groundwater on one of these space-time charts, and then a mapping of the techniques that we can use to measure groundwater. We did a review paper on remote sensing groundwater in 2022 Water Resources Research, that we have in situ data, which is very limiting and small scale. We've got INSAR, which can tell you something about groundwater depletion in certain situations, if you have enough clay minerals in the soil to represent subsidence. But then gravity as a technique is really priceless and invaluable. The current gravity missions, you know, there's a bit of a gap in resolutions there for the amount of aquifers we can represent. But future gravity missions, the concepts such as MAGIC that's been talked about recently as an ESA project and next generation gravity mission, really do hold the potential to close these gaps a little bit. So that's what we're hoping for as hydrologists. That would be really great to have. So I'll stop there. Thanks.
Thank you, GT. Thank you for this very interesting presentation. Also a surprise, but very nice. Question? Yes.
Hi, thank you so much. So now that I have a microphone, I may actually ask two very quick questions. The first one is, to what degree is the partitioning of a signal into different reservoirs just the model output? So just put that one on hold 1 second. You showed actually anomalies of GRACE and GRACE follow-on in one of the plots, but the latter had a much higher fluctuation variance, right?
Yeah.
What does it say about the accuracy of the earlier records, and is that just resolution?
So the accuracy is pretty much consistent with GRACE and GRACE follow-on, so no major changes in accuracy. I know what you're talking about. The second half of that time series is a bit noisier, and you're very perceptive to notice that. I think there was actually more noise in the other quantities that we removed, and this causes that residual to be more noisy. And then when we take the derivative of a noisy signal, it gets even noisier. So when we're looking at that delta groundwater DT signal, towards the end, it actually gets quite up and down. But yeah, really, really nice to notice that. Yeah, for sure. And the first question was, sorry.
Yeah, about how confident are you about the dynamics in the different reservoirs and the degree to which it's just the model output?
Oh yeah, the other reservoirs are horrible, really low confidence. No, because we have terrestrial water storage from Grace, pretty good, and there's quantified uncertainty estimates that come with that, measurement and leakage error from those estimates. When we estimate snow and when we estimate soil moisture, that's usually done with a numerical simulation, a model. And how those models define soil moisture, if you're a modeler, you know this, how you define soil moisture in a model, how deep your soil column is, where the bedrock is, the depth of bedrock, these things, they're all inconsistent. So we take a suite of models and we estimate an ensemble of soil moisture, but still that's the biggest error source, and the error budget is modeled soil moisture and modeled suite. These are highly uncertain for sure. Yeah, thanks.
Yeah, okay, thanks again, John.
Thank you.
We have to move on, so I would like to invite Daniel Blank from Hafen City University, Hamburg, for his presentation.
Yeah, thank you for the introduction. Yeah, welcome here to my talk. I will today talk about our joint analysis of remotely sensor moisture and daily satellite gravimetry, which by combining them may reveal better insights into the hydrological dynamics of the changes in the subsurface. So, first of all, standard products of Grace are monthly. So, however, the temporal changes in the temporal resolution of 1 month is too low to get any fast water mass changes. So for this purpose, we're using the daily ITSG Grace 2018 data, which captures also sub-monthly gravity variation. And we want to see if there can be also an added value. The trade-off between the number of observations used and the achievable spatial resolution makes it possible to generate daily data, albeit at a lower spatial resolution. To stabilize and restore daily signals with limited Grace observations, a Kalman filter is used, which introduces also some statistical information on the expected evolution of the gravity field, and in its process model, which reached then also a spatial resolution of, in this case, up to 500 kilometers. And this data were also already used successfully to characterize like major flood events or also to evaluate high-frequency atmospheric fluxes. So the research we do use now satellite gravimetry data from the Grace and Grace follow-on mission, which measure the entire water column as terrestrial water storage, which includes also, like we heard, also groundwater, soil moisture, surface water, snow. And on the other hand, remotely sensor moisture just observes the water content up to the very first 5 centimeters, and is referred to as surface soil moisture. And through vertical extrapolation, it's also possible to determine the root zone, and the products we use cover depths up to 1 meter. So let's see now which data sets are used. So for the surface soil moisture data, we use now level 3 data from NASA's SMAP mission and level 3 data from ESA's SMOS mission. We're also using the ESA CCI combined soil moisture product, which merge all available soil moisture data into one data set, which includes also the SMAP and SMOS data. And then we also looked at SMAP level 4 surface soil moisture, which is generated, it's based on the SMAP data, but generated by data assimilation. So it introduced also auxiliary information. And for the root zone soil moisture, we used 2 level 4 products, one based on SMAP and also generated by the data assimilation method, while the other based on SMOS using the exponential filter, which is kind of generated by approximate the root zone by delaying and smoothing the surface soil moisture. And yeah, the deeper soil layers, groundwater, all is monitored now by GRACE in the terrestrial water storage. We use daily data to see it, and we use now a time period from April 2015 on to end of 2022, which is the start of SMAP in April 2015. So we did also a previous study where we already looked at the global relationship between terrestrial water storage and soil moisture. We saw there are high correlations, even between soil moisture and even higher compared to the root zone, which are conceptually closer with a 1 meter depth to GRACE. And we saw that terrestrial water storage is shifted 1 to 2 months behind the surface soil moisture and then to the root zone up to 1 month, but this is also depending on the region where you're looking. This is like just an example for an exemplary grid cell here in India. So the other thing, we looked at the sub-monthly signal, so how much variations in the high frequency range from 1 to 30 days are still connected to soil moisture. We saw that there is still sub-monthly agreement. It's weaker compared to the full signal, but also again higher for the root zone, and during rainfall events and periods, the agreement increased even more. And there were also some regions with higher agreement, like the Parana Basin, Southeast United States, India, and so on, which showed also higher agreement. And this was all published this year in this paper. So the methodology for today, we wanted to see the behavior of drought and flood events. More drought events here in the presentation, not really flood events. So a time series of seasonal anomalies is needed. For this purpose, we also removed the linear trend to reduce impact of long-term signals like groundwater depletion in the GRACE signal. Then a seasonal signal, we were estimating an annual and semi-annual signal instead of a climatology, mostly due to all the GRACE gaps and the GRACE follow-on gap. So we calculated the seasonal anomalies by subtracting the trend and annual signal. And also to unify now the different observations, we have equivalent water heights and volumetric soil moisture. We have different soil depths. We standardize the data by dividing through the standard deviation for each specific day, which is in the end the mean deviation to the annual signal. So at first of all, we looked at the standardized anomalies, the correlations, just see already if they are fitting with each other and it's worth looking into. One of the first results is the global correlation between GRACE and SMOS. And on the right side, we see the cumulative distribution function, which all of the correlations collected. And one thing to mention also that desert regions are completely masked out because noise signal is dominating. And we did also a temporal mask where we removed days with snow and frozen soil. I won't go deep into a detail, but we observed agreement in higher in some regions. And when we move on now to the SMOS level for root zones, the agreement increased even more. For ESA-ESRIN, it's more agreement compared to SMOS level 3. SMAP level 3 is similar to SMOS. And if we move to the SMAP level 4 data assimilated product, it increased even more and even more than compared to the root zone soil moisture. So which again is closer with a 1 meter depth dynamic to GRACE. But throughout all the products, the region here in the Parana Basin showed also strong correlations, and this will also be the regions we are looking now more into. So this is the time series for the region here shown in the Parana Basin, and we see now here the surface soil moisture from ESA-ESRIN. One thing also to mention, the GRACE and GRACE follow-on gap is in every product deleted because yeah, actually there is data for the soil moisture, but we deleted it everywhere. And for the surface soil moisture, we see high fluctuations, and we see already some patterns of possible droughts from 2019 ongoing. To see if the highest and lowest matches also match with each other, we were calculating like the 5th and 95th percentile to see where drought and flood events might happen. And if we move now one step to the root zone, we see the signal gets dampened, yeah, but we still see agreement when it comes to this percentile values. And if we go then one step further to the GRACE data, it's even dampened more, but also here the percentile values agree with each other, especially from the period of 2019 ongoing. So it's also possible to calculate now an overlap of this percentile values on a global scale just to see where might be these extreme values, drought and flood events might be similar throughout the surface and root zone and then in grays. But I skipped this and I won't go further now. And so we plotted now every 3 signals together. We see they're quite fitting good with each other, especially from 2019 on. So we zoom into it. And yeah, we see the faster changes in the surface layer, and we can see it's get dampened with deeper layers. And also the magnitude is a little bit smaller for grays. We can see that there might be also like a longer drought persistence in the terrestrial water storage, yeah, and it needs a little bit longer going back to a normal level and have also like a slower reaction time. This is also the case for the onset of the drought and the storage loss over time. So what comes now is the next step. We find out how we can quantify this different dynamics. For this, we split the anomaly signal now in positive and negative, so it's storage surplus and a storage deficit. And this methodology is also mostly described here in Thomas et al. From 2014. And what now comes are also most of our initial results to quantify this. So we just focus now on the deficit here for grays. And if we look at for all the products, yeah, we can see on the left side the surface layer, on the right side the root zone and grays. We can see fast changing, this cascading effect from fast changing to longer reaction times, longer persistence in the root zone, and then compared to grays. The next step we did was then calculate a rate of change, like by calculating the time derivative of the deficit, just by a backward difference calculation, so value from today minus yesterday. And we can see this here. This is how it looks like now for the whole time series. And so where we have no variations, there's no deficit. And when we zoom into it here, we can see when we have like the declining trend, the storage loss over time, we have more storage loss values here. And then from November on, the increasing trend, we can see more and more storage recovery values. So this rate of change values, we are completely collected. Also, we calculated like an empirical cumulative distribution function out of this, which are now all the rate of change values for the deficit and giving like a good spectrum of this dynamic behavior during storage deficit. So on the right side, on the upper right, we see the storage recovery. On the lower left, the storage loss. And if we do this now also for the satellite surface soil moisture, we can quite see that all the 3 data sets of the remotely sensed soil moisture following a similar behavior, and the rate of change values are quite fast now. If we go then to the SMAP level 4 surfaces, dynamics is slowed down compared to the pure remotely sensed surface soil moisture data, and even then slowed down more compared to the root zone soil moisture. And what is noticeable here is now that the brown signal, the SMAP level 4 root zone, is slightly skewed distributed. So we have more negative rate of change values than positive. To keep it just simply, we decided to split these values now and just keep on the focus on the storage recovery, and calculated now a new CDF, which contains now just the positive rate of change values. So in there we can quite see, when we compare these different dynamics, we can see the fast changing in the surface layer, getting slowed down with the root zone and slowed down completely compared to grays. But yeah, from this point on, you can already compare these different dynamics with each other, which just is possible when we have standardized the data before. But what is also possible to choose a percentile describing like a likely rate of change. Yeah, it's just selected here for 90%, like describing a fast rate of change, and 50% the median value, like a slower rate of change. And from this, it is possible to calculate a quotient of the storage deficit from each point of the storage deficit, just to give like a likely time of recovery. It's like, this is then also possible. You would come to the same results of time of recovery if you didn't standardize the data before. So the time of recovery values are quite similar. So this is, but also just at the assumption, so how long from the deficit it would need to go back to 0. And this is just the assumption that it would be a linear trend. In the real world, it wouldn't be the case. And but it gives just an impression how long might the drought still persist in this layer. So we see here what this time of recovery means when we look now at the different percentiles, slow and fast. For going on, we just focusing on the 15% value. And yeah, we see now, like when we look at the SMAP and the small root zone data, these values decrease. And they are similar then decrease for the SMAP root zone and decrease then even more when we look then more to the surface soil moisture data. So at all, you can just calculate a statistic for this time series just to see at what level you see the higher values for the grays at the maximum of 80 days, then getting decreased values for the root zone and even decrease for the surface soil moisture. It's possible also then just to calculate the ratio to get an impression how faster is the surface layer compared to grays, which is in this case like 1 to 5. This is also possible just to calculate on a global scale, but this is also still subject to a lot of limitations. This cannot be claimed in general for every grid cell. And this has really to verify it with initial results of is there at all correlations, is there at all happening droughts, and so on. But in general, we can see we have the higher ratios for the surface soil moisture. And if I click through it to SMOS, SMAP, and also the data assimilated SMAP, we see the higher ratios. And when it comes then to the root zones, the ratios values are decreasing also on a global scale. So we have what we can also see as another limitation blocking the whole comparison. It's the leakage effect. We see it mostly on the ocean, that the ocean signals leak onto the land and completely change also the variability. And this is also the case for some lakes, so there's also still some work to do. You can also, the last thing is now just split the question and do it about storage surplus to look how the dynamics for flood events and how it's behaving there. And if there are some significant differences also from the storage deficit. So in conclusion, I just want to say, so we were looking now, we could see that the storage dynamics for deficits are faster in the surface, slowed down with the root zone, and then slowed down even more when we have the whole integration depths in the GRACE data. And GRACE with a higher temporal resolution can be therefore an added value for better understanding also this dynamics and the evolution of droughts and also for floods. We have a higher temporal sampling, but it's also essential to acknowledge that there's a regional and spatial limitations when we look at this 500-kilometer spatial resolution. And it's also just limited to drought and flood events, which have a big spatial impact. And very local extreme events are completely averaged out at the scale. As outlook, it's possible to extend this whole reference period to include more dynamics of historical droughts or floods, since the period from 2015 on is rather small. For this, we can also use the ESA-CCI data only because it's covering the whole grace period. And for root zone, maybe additional model data and ESA-CCI root zone data set would come very helpful also for this in the future to have this like a root zone product based on remote sensing. Then calculation of basin average and regional averages because better spacing matching the spatial resolution. And this is have all still to verify with actual dynamics of drought events and flood events. Like this was now complete for the whole time series, and that we verify this dynamics just also for some event-based times. But in the end, if we're looking forward, it's clear to improve spatial and temporal resolution. We hear that also before. For gravity observations, it's essential to have a better, understanding of this water storage dynamics. So it's essential we have this data. And for this, the next generation gravity mission and ESA MAGIC mission with 2 satellite pairs are from great importance to actually improve these resolutions and make, I think, a significant added value for a lot of hydrological applications. Yeah, finished.
Thank you. We have time for one comment or one question to Daniel.
Yes, Daniel, I have one question. So I've observed that in your analysis, you didn't include the surface water storage.
Yeah, it's true. It's also one limitation which you have still to take care of. For the daily, we would then need daily surface water storage values, which we have to harmonize also with the GRACE data in this 500 kilometer spatial resolution. But yeah, it's something we have also still to add to, because the surface water variability will also include. We see that we have the problems at lakes where we have also leakage problematics. So it's something to do. Yeah, but we didn't take care of it before.
Okay.
Any other question? Yes, please.
Here's also.
It's nice to see the analysis with the standardized anomalies, because actually you can compare the different components.
Mm-hmm.
But probably we should move on to make a kind of analysis as JT made. A lot of uncertainties, particularly to quantify the different components in terms of volumes.
Mm-hmm.
Probably we are there. We have a lot of data sets to be done that are there. And understanding how much water actually is in the different compartments is probably something that we should address.
Mm-hmm.
I don't know, what a comment.
That's also valid. Thank you.
Okay, thank you, Daniel. Any question? Any other question? It's okay, fine. Then the next presenter will be Mohamed Tourian from Institute of Geodesy, University of Stuttgart. So you have 20 minutes?
Thanks.
Okay.
Hi, everyone. So this is a work on Congo Basin, which Fabrice and I started 2-3 years ago, and we managed to publish it recently in Nature, Communication, Earth and Environment. So I would like to acknowledge all my co-authors, Omid, Nico, Benjamin, Rafael Chimanga, who did a lot of advice on the Congo, Adrian Paris and Stefan. So Congo, as opposed to Amazon, is a rather much complexer basin. So I would like to study this picture together with you. So you see here, first of all, the first things that you would probably realize, Congo Basin is kind of straddled to north and southern hemisphere. I mean, that by itself complicates everything. So you have Cuvette Central here in the middle that it's kind of sort of a resistor by itself. And then you have in Lualaba Basin, you have a lot of lakes and so to say, wetlands. So you see, for instance, this Bangvelu, you have a huge wetland, and then inside there would be a lake, there's a lake. So it's a very complex environment if you want to study from the hydrological perspective. And it's actually, it is very complex, and there are some data there were some data in the past, but nowadays it's kind of underrepresented. For instance, if you want to find out the in situ data in the Congo basin, you hardly find good updated data. And there was even a paper, a nice paper by Doc Alstorff, even kind of made some statistic how many studies have been done over the Congo, how many studies over the Amazon. And of course, nowadays got better, but still, if you compare the number of studies or understanding of our Congo basin, that's not as good as Amazon. But the starting question that we had was how much water can be drained from the Congo basin? I mean, that's the question I want to answer. And that was the motivation of our work. And I would like to answer this question basically, of course, I would like to use GRACE, but from a perspective of by benefiting from relationship between runoff and storage. So imagine you have a basin. Well, basin, of course, you can imagine by all these talks that we had just now, water storage would change. Then you have discharge. So if you could imagine from each part of the basin, you would have storage, you have runoff. If you accumulate all the storage in a basin, then you would have a time series. If you accumulate, well, if you measure runoff or discharge at the gauge of at the outlet of the basin, then you have such a time series, which often you see annual and semi-annual behavior in it. But if you try to plot these two signals against each other, you often, if everything goes well, if nothing further complicates the scenario, you often see such a behavior. So, and that's something very simple and interesting at the same time, which has two components, two important, so to say, variable or parameter. Namely, one is the time shift. So you can imagine water comes in a basin. It takes a while that it gets discharged out of the basin. And then, of course, that would be the time shift that you see. And that's exactly this kind of, so to say, ellipsoidal, so hysteresis behavior that you see in these plots. So that means if you remove this delta t by any way, so you get kind of linear behavior. And of course, you have this conversion factor, like, I mean, here is abbreviated as tau. And that's, so if you consider discharge is a sort of, the unit of discharge is cubic meter per second, and cubic meter per second, and at the same time storage you have often meter or so. So if you want to if you have a conversion factor between these two variables, the unit of this tau should be time in principle, and you can consider this tau as a sort of time constant, or you can interpret it as how much time it does take for water to be drained from a catchment. So that's how you should interpret these two parameters. So let's put it in math. So that would be very simple. So you have discharge on the left side, then you have storage. So that's basically the 0 point, and then the storage plus this delta t. And then if you know all these parameters, then of course you can model discharge using storage or vice versa. But there is a hidden, or there is a third parameter, which is much more interesting probably than these two. So we have this delta t, we have this tau, which said it's simply a conversion factor. But much more interesting than these two is this S0 parameter, which means, I mean, if you consider this model, so that means you can draw a line, and there would be a sort of storage at which the discharge would be 0. I mean, this would not happen in Congo. This would not happen in any of basin. So, but practically it means at one point, the entire water in a basin is discharged out, and there is no discharge from that catchment anymore.
So in fact, this S0 is nothing else than the total drainable water storage of a basin. So that means if you would be able to model this, then you can quantify how much water a catchment has. So as simple as that. I mean, of course, I say simple. Amazon, I mean, that's how different basin would look like if you try to do that. So for instance, in Amazon, as we just illustrated, or the boreal catchments, the scenario is much more complex. So you have a frozen time period, and then a melting period, and then yeah. So that's a bit complicated, but still one can manage to turn it to sort of line and even calculate S0 there. And over Niger or kind of seasonally dry tropical, the scenario is different. So here you see, if you follow the month, if you follow the month, so it's kind of counterclockwise, but for a case of Niger, you would have a clockwise behavior. Okay, all intro. We have done 2018 together with JT, the analysis, and that time we have been able to quantify this S0 parameter, and we came up with 1,800 cubic kilometer as total drainable water storage of Amazon. And then we wanted to actually try the same for Congo, but we have to understand that Congo, as I said, is much more complex. I mean, the same story, but here you have wetland. Of course, that's not, I mean, you have wetland, you have lakes. Of course, you have also those in Amazon. I don't mean that in Amazon you don't have wetland, but the dominant signal, or the Amazon is so shallow, everything is on surface, that would not really dominate the behavior between storage and runoff. But in the Congo, because all these lakes are much larger and wetlands are much larger, that makes everything much more complex. That means, and even you have some lakes that are kind of decoupled from the storage. So they are kind of not connected to the discharge system. So you have a different situation. Here we have introduced one parameter, or drainable water storage anomaly. And then that means simply S, I mean, from the total water storage that Grace would monitor, you subtract the wetland part and lake part. So you remain with this kind of this kind of storage that is super connected to the discharge system. If you do that, you get such a complex behavior. So that's not as so to say nice as before. You have a sort of clockwise behavior, but suddenly there is a counterclockwise behavior for a couple of months. Let's try to understand where does it come from. So if you see the time series of total water storage, that's the Grace time series. The second time series, the wetland water storage. The last one is the lake water storage. And you have to read these time series so that we have calculate the wetland water storage for the entire Amazon, and that's the aggregated time series that you see here. And for lake, the same. So all the lakes are accumulated, and you have these time series. So first of all, from the time series of Grace, what you could capture, you have the first peak, which belongs to the northern hemisphere, and the second peak, which belongs to the southern hemisphere. And so that means already the idea of, so to say, a clean seasonal behavior is gone. And of course, you see that because lakes are distributed mainly in south, you see that the peak of lakes would really match up with the southern hemisphere. But then if you plot over the entire years, then you see such a complex behavior. But then if you take the mean monthly of all these years from 2002 to 2019, then you have this black curve or black behavior, which I've illustrated. And the months that make things really complex is from February to May in principle. So that's if you see the mean monthly grace, again, mean monthly discharge, you would realize that, yeah, so there are some, in all these months, grace is ahead, and then the other vice versa. So we kind of developed a methodology, basically try to actually remove the time lag, but this time, unlike Amazon, the time lag was removed for each individual frequency separately. So I don't want to actually go that much in detail, but we managed to give to receive this linear behavior between storage and runoff. And at the same time, we had to generate a lot of discharge ourselves using satellite altimetry, and so a lot of work went in. But there was one important point. So previously, I introduced this variable drainable water storage anomaly, which I subtracted lake and wetland from it, and assumed that that is really connected to the system. But that is really an assumption. I mean, you can't, you would never sure about a lake to be completely disconnected from the system or connected to the system. So that means in order to account for, so to say, any approximation in that, we have made the calculation for two cases. One with total drainable, with total water storage anomaly, where we did not subtract lake and wetlands, and the other where we subtracted lake and wetlands, and anything we calculate, any storage or drainable water storage that we calculate from this drainable water storage anomaly, that would be the, so to say, lower bound, and the other would be the upper bound. So that's how it looks like. As I said, so these are the mean monthly. If you fit the line, then you can calculate the total drainable water storage, which turns out, and if you calculate, this is the equivalent water height. If you multiply with the area, the amount of water that Congo has and can be drained is 476 cubic kilometer. That's, yeah, I mean, I don't say anything that you could digest the number. Yeah, and that's, so that's the lower bound when you remove the lake and wetland, and the upper bound would be 502. So that means if we want to say something about freshwater availability of Congo, that would range between 476 to 502. And of course, in our calculation, we involved also the uncertainty, and then you report also an uncertainty for all these numbers. And of course, if you can always validate your result when you do the same calculation on subbasins. So when you do the same calculation on all these subbasins, of course, there are a lot to be seen in these, a lot of interesting phenomena in all these subbasins, which are completely different from the Congo itself. But if you do the same calculation and add them up, then from the subbasin analysis, we got something about 503, which is actually staying the same range of uncertainty as the calculation for the entire Congo, which means that puts some validity in our results. But of course, we wanted to also do some plausibility assessment. The first would be to compare it with Amazon. So that's the value that we have calculated over Congo, and that's what we got in 2018 for Amazon. And if you just simply calculate the ratio, that's 25%. And then if you look at the average discharge of these two, that's 20%. And the TWSA, the amplitude of grace itself, it's also, so all in all, and also if you see the amount of recharge into the Congo and Amazon, that also stays at the same level. So the fact that these percentages are not way off from each other puts some credibility to our estimate that we are not completely off. The other way would be to look at the driest value of each degree grid cell in Congo from the GRACE data and then sum it up and see if we are below, I mean, if our value is larger than this sum, which was the case. So with that, I would like to conclude. So the number, as I said, the Congo Basin total drainable water storage is ranging between 476 and 502. And the distribution is also interesting. 63% of Congo's freshwater resources are stored in southern basins, in Kasai, about 220 cubic kilometer, and Lualaba about 109 to 169. And the hydraulic time constant, that tau factor, which I mentioned earlier, the amount of time that Congo needs to discharge its entire water is about 4 months, which would never happen. But I mean, who knows? Maybe happen. I don't know. You should never. Okay. Outlook and recommendation. So the method can be applied globally. There's no limit to that. I mean, but there are some challenges. You need in situ discharge data. You need to quantify surface water storage. You need to, I mean, if you go boreal, in the boreal region, you need to quantify surface water equivalent and many other parameters. So it means if you are equipped with the data, you can apply the methodology. It's very simple. But of course, one remark as previous talks, future missions, for instance, MAGIC would contribute to such a work a lot. So that means your calculation of total water storage, the drainable water storage would be much better, especially in smaller basins. And yeah, another recommendation would be more studies on Congo because it's very interesting region, Benjamin, as you could imagine. Yeah. So thanks a lot for your attention.
Thank you, Mohamed, for this very nice presentation. Interesting studies that have been conducted in Congo Basin. So any question from the audience? Yes, David?
MJ, that was fun. Listen, I'm trying to wrap my head around what's the drainable water storage. And the first thing that comes to mind is, well, if discharge is 0, that means the rivers are not flowing, so there's no water in the rivers.
Exactly.
So that would mean it's primarily groundwater and maybe some lakes that are no longer flowing into rivers. Like, how do you picture what that means? Thanks.
That's a very good question. Yeah, I think once I had a definition for that, the amount of water that gets out of a basin without extra energy. So that means even so, because groundwater is also, I mean, you get base flow and would be also contribute also to discharge, but so this 476 cubic kilometer is the amount of water that if no rain happens in Congo would discharge out of Congo. So that means, and of course there would remain water in Congo that you need to extract from groundwater. And to be precise, I think would be young groundwater in that terminology. I mean, that consists young groundwater and but yeah, the exact definition I don't have. It's kind of.
Yeah, you know, people have asked me the same question, like, what is the purpose of total drainable water storage? And I think that a good way to think about it is it's all the dynamically active water in the basin. So if water is locked in groundwater, it's not interacting with the surface. Or if it's sitting in a lake and it's actually not draining, it's just in a derrick sitting there, it may be not interacting with other hydrology in the basin. Then the implication of that is like modelers, like land surface modelers, you know how much water is required to be in storage in order to generate that runoff. So on a land surface model, a coarse model like that for an entire basin, that really should be the amount of dynamically active water that exists like in that basin, right? So that's one way to think about it. One question for you. also because I know of your expertise in river altimetry.
Yeah.
Do you think with the advent of SWOT, there's opportunities to also increase the resolution and maybe even do something like this on grid scale or at least small basin scale that could feed more directly into models and things like that?
That's a very good point. I think when SWOT is there, so that would really contribute to that, because surface water storage can be quantified in principle way better, and I mean that's the basic. Of course, you have a better surface water storage, but I can imagine also it would add. There's another add-on to the whole game, namely you would start better the dynamic of the storage and runoff, because you have, so to say, you can actually picture that for the entire. Yeah.
Last question, maybe. Okay. Yes.
It's a super quick one. Where is evaporation in the story exactly? So you stop rain, you discharge all the water. Is evaporation assumed to be zero, or where is it in the equation?
Super quick answer.
I don't have super quick answer, so maybe chat later on.
Okay, thank you. So then we'll move to the final presentation of this session with Serena Seola from University of Bologna.
Is it working? Okay.
You have 20 minutes.
Yeah, okay. So good afternoon, everyone. My name is Serena Ceola from University of Bologna, and today I'm presenting a research that was basically carried out by postdoc Irene Palazzoli, the second author in this slide. The topic of my talk is related to changes in surface water extent and the influence of anthropogenic but also hydroclimatic drivers in these changes across the Caunus. The main motivation of this work is basically related to the influence that is played by climate variability, but also socioeconomic variables that can play a key role in controlling surface water extent and changes in surface water extent in time. So they move their location in time. So basically I'm focusing on natural factors, low climate variability, meaning that alteration of the global hydrological cycle. So spatial and temporal variation of all the variables in the hydrological cycle. So from precipitation to temperature, evapotranspiration, soil moisture, and then discharge. But also I'm considering the development, socioeconomic development, so how urbanization processes or population dynamics, irrigation associated to food production, but also the presence of dams and reservoirs, how they can alter this surface water extent. So our research objective was exactly that one. So to try to understand, analyze these changes in surface water extent and possible drivers of these changes. And the study period focused from 1984 to 2012, according to the available data we use. And the research is also published, was recently published in May this year in Environmental Research Communication. So our goal was, first of all, so we had 3 research questions. So basically, we wanted, first of all, to quantify this change in surface water extent, but also the change in anthropogenic factors, in hydroclimatic factors across the Caunus. Then we wanted to analyze if there was any remarkable or spatial pattern controlled by climate classification, climate variability. And then at the end, we wanted to analyze the influence of changes in anthropogenic and hydroclimatic drivers in changes in surface water extent. So basically, we have our dependent variable, so the surface water extent. Then we consider 3 different anthropogenic factors. So we considered built-up, population, and irrigation. And then we had a couple of climatic factors, so we consider precipitation and potential evapotranspiration. As I mentioned before, the analysis focused on the contiguous United States because we already did a previous analysis on the same area, so we already were using similar data. The reason also for selecting this area is because it's characterized by remarkably heterogeneous drivers in terms of both hydroclimatic but also socioeconomic conditions. So we span from wet to dry regions, especially varying topography and surface water availability and remarkably different levels of urbanization. Our analysis was performed at the river basin level. So you can see from this map the river basins we consider in our analysis, so 204 river basins that correspond to the 4-digit hydrological units. And then also we overlap to these river basins, we consider climate classification according to a Copenhagen climate classification as depicted in the map. Regarding the data, as I mentioned before, we were interested in analyzing changes in surface water extent. So if there is water or no water, not about how much water do we have, okay? So we got this information from the global surface water data set, and in particular, we selected the layer that is called the surface water occurrence change intensity layer. So basically, this layer shows where surface water occurrence increased, decreased, or remained constant in the study period from 1984 to 2020. But this change is basically related to by comparing two subperiods, before 2000 and after 2000. So this layer provides a percentage, a direction of change, and by selecting a threshold, a 75% threshold, we were able to identify pixels that experience a surface water loss, highlighted, so the red pixels here, and the pixels that experience a surface water gain. And this is a zoom in over the Great Salt Lake City. Then we consider built-up area, and we derived built-up area from the global human settlement layer dataset from the GRC. So basically this this dataset provides the multi-temporal evolution of built-up. Okay, so since our dependent variable, the surface water extent, was considering two subperiods, before year 2000 and after year 2000, we needed to identify the evolution of the built-up area before the year 2000 and then also the evolution afterwards. So, and the dataset was allowed us to do this. The same also applies for population. So we derived population estimates from, again, the global human settlement layer, that basically describes the distribution in space, but also in time of population observed in different epochs. And for irrigation, we derived estimates of irrigated land from the irrigated agricultural dataset that supplies irrigation data for 4 specific years, 2002, 2007, 2012, 2017. So we took 2 of these 4 years as representative of our 2 subperiods. I still have a couple of maps. The first one that I'm showing now is the mean annual precipitation. So we computed mean annual precipitation from the DayMed version 4 dataset. And we also computed the mean annual potential evapotranspiration from HPET dataset. So, so these are all the data we use for our analysis. The goal was, again, analyze this change in anthropogenic factors, in hydroclimatic factors, and see if there is an effect on changes in surface water extent. We performed this analysis at the river basin level, and then we compare what happened before year 2000 and after year 2000. So the changes in surface water extent at the river basin level are computed as basically a balance between what was gained in that specific river basin and what was lost in that specific river basin. So we have a generic river basin with a given number of grid cells, and then we computed how many grid cells experience a gain and a loss in order to compute a net balance. Then we, regarding the anthropogenic variables, we compared what happened before and after year 2000, so to see if there was an expansion in built-up area or if there was a reduction, and this applies also for population and irrigation estimates. Regarding mean annual precipitation and potential evapotranspiration, we had annual values. So we had monthly value and then aggregated at the annual level, and then we computed these long-term averages for the two subperiods, as shown in this by these formulas. So now I'm moving to the results and show basically some maps that highlight how these changes in surface water extent occurred and characterize river basins across the Carnus. So from this map, you can clearly see that the majority of river basins in the Carnus observed a gain in surface water extent. So you see that the color bar spans from the red, so meaning that we have a loss, from blue we have a gain. And the loss basically characterized the southwestern part of the US and also the northeastern part of the US. In order also to see if there is any climatic patterns that control this variability, this spatial variability, you can see from this box plot on the right hand side that we classified river basins according to the main climatic classification. So actually temperate river basins present a slightly larger increase in surface water extent as compared, for instance, to continental and arid river basins. Since we know that variations in headwaters can also play a role in what is happening at a larger scale, so by considering all the contributions from different subbasins, we basically aggregated and we repeated the analysis at a larger aggregation level by considering water resources regions as depicted in the map here below. So the results that we obtain from this map, of course, reflect what we obtain at the river basin level, but also they confirm recent independent findings that revealed increasing trends of river discharge across the Mississippi River and a reduction of surface water extent, and so river discharge across the St. Lawrence, Rio Grande, and Columbia rivers. Then I'm showing similar maps also for the anthropogenic drivers and then also for the hydroclimatic drivers we consider. So for the built-up, all the river basins in Carnus experience an increase in built-up area, with the largest increase across temperate river basin, followed by continental river basins. Similar results are obtained for population, even though some river basins experienced a decrease in population. And again, by looking at the box plot, we have temperate river basin characterized by this larger increment in population. Concerning irrigation, we have an increasing irrigation for 67% of the Carnus, and with remarkable reduction that characterizes basically the southwestern part of the US. Regarding the hydroclimatic variables, from our analysis, so the changes are quite obvious, but then of course we see that the central and eastern part of the US experience an increase in mean annual precipitation, with largest increment in continental and temperate basins, and overall the Carnus basically experience increasing potential evapotranspiration, and of course across the arid river basin we have the largest increments. So given this spatial distribution of changes and these climatic patterns, then we try to see if what was the contribution of drivers, anthropogenic and hydroclimatic, on changes in surface water extent. First of all, we check for cross correlation among drivers, and we so there was a sort of correlation between built up and population, but then that was low, so that we decided to continue keeping all the 5 drivers in the analysis. The correlation, as you can see from this map, is quite low to mild. Only arid areas present quite larger values between the gain in surface water extent and change in population. But I think that the most interesting result is related to the spatial overlap between the potential contributors to changes in surface water extent. So now I'm showing a couple of maps. In this map, you see the river basins that are experiencing a net gain in surface water extent. So the majority of river basins, as I mentioned before, are experiencing this net gain. So we are talking about 169 river basins across 204. Then On the top of each river basin, we put a symbol that represents the potential influence, potential effect of the drivers we consider. So we assume that we can see a net gain in surface water extent if built up is decreasing. So if we have decreasing built up, decreasing population, decreasing irrigation, increasing mean annual precipitation and decreasing potential evapotranspiration can contribute to a gain. Okay, so if these conditions are fulfilled, then we put a symbol on the top of each river basin. And here it's quite remarkable to see that basically a striking characteristic is that the majority of the river basins that experience a net gain, we found that the increasing mean annual precipitation played a key role. And this was valid basically almost across all the river basins, but especially across the eastern part of the US. Okay, so a net gain in surface water extent is mainly related to increasing mean annual precipitation. We had here a net gain in surface water extent in the western US and along the coast because there was a reduction in irrigation, but this probably is related to the use of groundwater resources, which were not included in this analysis, okay? Then I'm showing a similar map, but this map relates to the river basins that experience a net loss in surface water extent, okay? In this case, I'm hypothesizing that increasing built-up contributes to a loss, or increasing population can contribute to a loss in surface water extent. The same applies for irrigation. The same applies for increasing potential evapotranspiration, while a loss could be due to a decreased mean annual precipitation. Okay, so I'm overlapping all these conditions and see what the results. So basically, from this spatial overlap analysis, we see that basically the built-up, but also the potential evapotranspiration played a key role because they were found in all the river basins that experienced a net loss in surface water extent. We identified two different features, basically in the northeastern part here, where we have a loss. This loss is basically associated to the expansion of built-up, the irrigation, and the increasing potential evapotranspiration, while there was no effect provided by mean annual precipitation. In the southwestern part, mean annual precipitation is, in this case, playing a key role together with built-up and potential evapotranspiration, while irrigation is influencing only half of these river basins. So now I'm moving towards the conclusion. So the goal of this research was to analyze, to detect possible impacts associated to anthropogenic factors on climate variability, and how these factors can control changes in surface water extent. It is important in order to prevent and control alterations of the hydrological cycle and also towards the supportive adaptation strategies. This research presents some limitations that I would like to acknowledge. So as I mentioned before, we do not consider groundwater, so we simply relate to the surface water detection, okay? Also, we are not considering water volumes. So again, we did not use estimates of discharge. We performed this analysis by considering changes between two different epochs instead of performing more detailed analysis in terms of temporal resolution. And also, one limitation could be associated to a possible underestimation of irrigated areas, especially in humid regions from satellite images. But despite this limitation, we were able to find that basically the net gain in surface water extent was mainly related to increased mean annual precipitation in the majority of the canons, while urbanization and increasing potential evapotranspiration were the most widespread factors that influence a net loss in the canons. Also, regarding this last point, basically the same results were obtained from another paper that analyzed the effects of climate and irrigation on GRACE estimates of water storage changes in US major aquifers. So the total water storage that also includes surface water and now we consider only surface water. Some future perspectives. So I mentioned at the beginning that also dams and reservoirs can play a role in controlling changes in surface water extent. So we preliminarily analyzed the potential role of reservoirs and dams. And what we found was basically that dams have significantly influenced the gain and not the loss of surface water extent, especially in the continental, in river basins characterized by continental climates. And the last slide is basically the recommendation and outlook from a broader perspective. So what we did not have here were estimates of, so we did not use estimates of discharge. We did not have estimates of reliable estimates of water withdrawals, which would be much beneficial for analyzing in a deep way the human influence on water availability. I think we need to measure and then model. So this is why we need data. We need to measure the mutual interactions between climatic variables, hydrological variables, and also anthropogenic variables. I'm also focusing my research on human adaptation to extreme events, so floods or droughts, if people are moving according to these extreme events. So we need data that in order to prove these hypotheses. And I'm also copying one of the suggestions that were shown by Angelica yesterday. So also we need platforms for analysis of big data. And with this, I'm done, and I thank you for your attention.
Thank you, Serena, for this nice presentation. Any question in the room? Yes, please. Can you come to the mic, please?
Hello, Milias Daras from ESA. Thank you very much. Very interesting presentation. I'm just curious why you chose, what are the limitations to include the groundwater estimates in your research? And why haven't you done this yet?
Because we used the surface water data set. We were using the same data set for a different analysis. So we decided also that the previous analysis focused only on anthropogenic impact, on the influence of urban areas in surface water depletion. And we decided also to include the possible role of hydroclimatic variables. So this was the reason why we did not consider groundwater in this specific research activity. But one of the next steps is also to include groundwater.
But you're aware about satellite gravimetry products providing this information?
Okay. Any other question? Yes, maybe one. Yeah.
Mm-hmm. Okay. So we did not include land cover changes in this specific analysis because we decided to focus first on the built-up evolution. And as you saw, basically built-up increased everywhere. While we had some changes in population, but remember that population, so the maps that I was showing before referred to the river basin. So it is a sort of spatially average behavior of what is happening in that specific river basin. Okay, so meaning that I'm not considering the local variability. Okay, so maybe it is not shown because it is aggregated. Okay, but thanks.
Yes. Okay. Thank you, Serena. So we will take this time now to have some brainstorming about some set question that we prepared before the coffee break. So we have prepared four questions, but due to time remaining, I think we can pick up two of them and then try to.
Yeah, Fred, we have been very, very bad in keeping time.
Technology issues at the beginning.
Yeah, we had also some technical problems. So as Jérôme Bavanis repeatedly insists on in his introductory speech, we special agencies need, and ESA in particular, in our case, need some feedback from hydrological community to shape the next call, see what topic should be addressed in priority or what should be also investigated out of intellectual curiosity, which might lead also to interesting discoveries. So we don't have so much time, unfortunately, as Benjamin said. I was happy to see actually two presentations concerning groundwaters, and maybe that's one point I would like to quickly put forward. So I think that's point 3. You can read it. But maybe a point as I would like to have feedback on is, is Earth observation precisely so can have a significant contribution here. So to quantification of groundwater, but also the characterization of the dynamic replenishment, pumping as well, and on this. And very likely in the next year or year after, some I don't know, probably some ITTs from ESA will come on this topic. So I would like to hear from you.
Maybe a bit of summary if it helps you guys, because there's going to be probably a report or something like that. You know, if we think about hydrology really simply, you know, like a bucket model or something, it rains, and then later there's discharge that comes out, and everything that happens in between is hydrology. So like this last talk on surface water formation, very interesting, right? But what are the processes that drive that surface water formation? It would be different in very dry climates versus really wet climates, where there's an active interaction with the water table versus a dry climate where there's no active, you know, interaction with the water table. And we have observations now pretty much around every aspect of these variables in the water cycle, as Elias just said, that we could say, all right, we kind of know something about groundwater and how it varies. We know something about soil moisture and how it varies. We have precip, we have surface water. That is time probably now to start doing integrated analyses where we're starting to look at these processes and have better process representation in our models, because we have these different variables that we can now observe simultaneously. And I think one of the biggest obstacles in that, something that we don't really talk enough about even at this meeting, is that sometimes what we exactly observe from space is not the same variable that the model actually simulates. So for GRACE, obviously, I mean, while we're seeing terrestrial water storage, it's hard to get that exact representation, adding everything together in a model. But I think one of the first lessons we're learning from SWAT is that river height is not the same thing as discharge. So when we observe something from space and we simulate it in a model like runoff, that translation between what we simulate and what we observe as hydrologists is really one of our biggest remaining challenges now that we have all of these observations.
Thanks.
With respect to item number 3, groundwater monitoring network, design of groundwater monitoring networks is an important issue that has to be addressed in water resources management. And I think if the issue of downscaling GRACE data can be solved, then Earth observation can be an important, can play an important role in that, in designing groundwater monitoring networks and determining where our monitoring wells have to be placed, because Earth observation can tell us where in the basin the groundwater changes, where in the basin it does not change that much. And we would like to place our groundwater monitoring wells in places where groundwater changes. And I think Earth observation can play an important role here.
Thank you. Yeah, maybe I can also put the question differently. How critical are in situ data for groundwater monitoring? Because as you say, we can have definitely take the problem as a whole. So we have all the compartments except groundwater. So by closure, we might have some insights into it. So that's with Earth observation, but maybe we need also in situ data, and this might be also maybe a problem. Luckily, ESA can also fund some in situ, some field work, but okay, maybe that's a bit tricky. Yeah, that's also a question I throw. Like, in your experience, do you have problem accessing to this data? How many data set is there? I'm novice, so here as well. I need to know how feasible such study could be. Any input on that?
I don't know if okay. I will just raise another point, maybe, concerning the issue of the lack of groundwater monitoring, about the validation of the derived groundwater variation. Has many presentation before here were presented. So there is a possibility actually for now to derive groundwater from GRACE signal. We have a few river basin where this derived groundwater variation can be validated with piezometric data. So how now in basins where we don't have piezometric data, how can we accept, I will say, these results from GRACE, you know, from GRACE derived groundwater variation? How can we accept it? Yes, how in the community, you know, we can deal with that issue. I don't know if, yes, please.
So as far as I know, groundwater is something that is something that people wait and see for a long time. And if you want to take actions, the problem with the data latency and the temporal resolution of GRACE is not a problem. I think the problem is when you want to calculate groundwater from GRACE, you need to consider the errors of the other compartments. And at that point, you realize that you need better estimation of other compartments. The GRACE see the whole, and you are removing all other compartments with a huge uncertainty, and in the end, you get a huge error. And I would say and to answer to your question is when we do not have any in situ data in one region to validate GRACE, I would say it depends if you already had enough in situ or remote sensing data for a good model for other compartments. If you have a good model for other compartments and the error of the other models are good enough, then you can trust more. If you have in situ data of groundwater in regions, but the models are performed really poor, it doesn't matter. You're still having a really low quality groundwater estimation.
Thank you.
The take on this one.
I just want to say quickly, this is such a good question because I think the answer, you know, there's like a traditional way of thinking that we should be validating remote sensing data. And of course, we should be validating remote sensing data. Of course, we should. But really, so many remote sensing observations give a different perspective than what in situ data give. So with river flow, for instance, you can have gauges in a river, of course, but what SWAT sees is going to be such a different perspective on that river because it's going to be sampling different sections of that river at different times. And so if I was a river modeler, I would want both. I would want the in situ data at the mouth. I would also want to know what's happening upstream and how runoff is contributing to the runoff at the mouth. And in order to do that, I will never have enough in situ data. So I also need the remote sensing data. The same thing with groundwater. GRACE will never give us groundwater change at the level of a well, a specific well. But gravity in general is really useful for understanding big changes over entire basins. The studies that have been done in Northwest Pakistan or in the Central Valley in California that tell us for the entire aquifer how the groundwater is declining. Even if you aggregated all of the well data that you have, you would never accurately get that full volumetric change of groundwater for the entire aquifer. So there's many conditions where we really need both in situ measurements and the satellite measurements. And it's not a validation issue. It's just that they offer orthogonal pieces of information which both have value.
Yes.
Just to add to what JT just said, fully agree. Just to say also that GRACE gives a phenomenal accuracy at the special wavelengths that it observes. So it's really useful and unique observation that we should maintain, I think, for the hydrological research. And I think there are level 3 groundwater storage products available given at Gravis portal with uncertainties attached to it. So the modelers know more or less the internal accuracy of these fields. And of course, validation, of course, important. And you cannot have enough of in situ data. But just to stay here, that we know the uncertainties from these level 3 products on the groundwater storage. And of course, signal separation, as was mentioned before, is of paramount importance to do it to assess what is the effect of its contributor that is separated to arrive to the groundwater.
I should add to that that's groundwater quantification, that estimation is not only a closure problem, but it can also be better constrained by also process understanding. And I refer here to Mohammed's presentation where the estimation that you had of this, so S0 includes certainly also groundwaters, right? So there are also some process that can help better quantifying this quantity. So I don't want to get stuck in groundwater, and I think I should also close the session quickly. Otherwise, tea and coffee pots will be empty when we go there. There were a couple of other questions, but of course, feel free. I mean, if you have ideas, scientific question that you think can fit in an ESA project, and you want to see it next year in the coming years, yes, then you feel free to email, to submit your suggestions. There were, for instance, this PUB challenge. So make discharge prediction relying solely on EO data. I think we have already seen a couple of presentations showing that's feasible, but of course there are still a few issues to deal with. Yes, yes, please.
That you don't measure, for example, irrigation. Irrigation, you give information, perhaps it's summer, perhaps it was the people that the water from of the like it's very difficult to quantify it to arrive in the whether they try in Germany to get to understand how much irrigation
Yeah, that's a remark we've already collected. That is, of course, we have this wishful list of things that we would have available, and that's one of the things to make such a data set, so collect the data so that it's freely and easily available. For instance, irrigation, the irrigation field, so the time series of irrigation over a given area. Yeah, that's definitely something we can try to work on. It's not EO per se, but that's useful. Yeah, I agree. Yeah. Yeah. Any final comment? Otherwise, I think we can all run for a coffee break. Thanks.
Okay, thank you for
again.
participating.
So I think I will start, maybe we'll start by introducing ourselves. My name is Fia Ermida, and I work for the Landsaf at the Portuguese Institute for Sea and Atmosphere.
And my name is Cynthia Bonanat, and I work for the Plus Atlântico Lab here in Portugal.
So our first presentation is by Jacopo Dari. Jacopo?
Hello. Can I start? So, good afternoon again, everybody. I'm Jacopo Dari. I work at the University of Perugia, but I am also research associate at the CNR-IRPI, based in Perugia as well. The title of my contribution today is Regional Scale High Resolution Estimates of Irrigation Water Use from Satellite Data. First, I would like to point why it is important to study irrigation when dealing with the water cycle. So I will start with the question, which is why irrigation? Basically, because among the human activities that somehow interact with the water cycle, irrigation is the most impactful one. But despite this, in general, we don't have detailed information on irrigation dynamics. Irrigation dynamics means irrigation, where and when irrigation occurs, but also, and moreover, I would say how much water is used for irrigation. So these are basically key questions of this research line that still represent a challenge somehow, and which are also the drivers, of course, of this work and of the research that produced the results that I'll show you. But the same questions were the drivers of also the drivers of an ESA project called Irrigation Plus, which was also presented this morning at the Science Cluster for Hydrology for the people that were in this same room this morning. Basically, the project, this Irrigation Plus project, aimed at developing Earth observation-based algorithms and techniques for monitoring irrigation from space. So monitoring irrigation, again, it means irrigation detection, so mapping and timing, and irrigation quantification. So try to answer the question, how much water we use for irrigation. Actually, the results shown in this presentation are a fruit of this project mainly. Then we have also some new results. The method with which we try to estimate irrigation from space is the soil moisture-based inversion approach, which is a method that relies on the inversion of the soil-water balance for backwards estimating the total amount of water entering into the soil. Over agricultural areas, this amount of water is supposed to be rainfall plus irrigation. So basically, if we remove the total amount of water that enter into the soil according to a soil-water balance, which is basically forced with satellite soil moisture, now that should be in principle able to track a change that is due to irrigation. And we remove from this amount the rainfall. As a residual, we estimate irrigation. So the method is pretty simple. The basic equation is the one reported in the top of this panel, where there is the soil moisture variation in time, which is equal to irrigation plus rainfall minus drainage, surface runoff, and evapotranspiration. In our method, we write each component of the balance as a function somehow of soil moisture. So we try to link each term of the equation to soil moisture, which is our main input, but not the only one. And then actually, as I was explaining, we are able to, with the solving equation, which is the last one, we are able to estimate the total amount of water entering into the soil. Then as a last step, we remove rainfall and we obtain as a residual irrigation. The results that I show you in the following slides are obtained with different soil moisture and evapotranspiration data sets because it depends on the area, on the specific area. But the used data sets are, however, Sentinel-1 soil moisture from RT1 produced at TUVN at 1 kilometer. And then we have also results over Australia with Cygnus soil moisture at 6 kilometer. And within the Irrigation Plus project, so the first version of the irrigation water use data sets, we have estimated, we have used the coarse resolution GLIM data, but then in another project, we have also updated this input with high resolution GLIM data. Before going to the results, a slide on the calibration, because as you can see from the solving equation, we have 4 parameters in our model to be calibrated, which are the soil water capacity expressed as Z with a star, A, B that are drainage parameters. They play a role in the drainage term. And then we have a factor F for adjusting the evapotranspiration contribution. So how we calibrate this parameter? Well, usually we adopt a first guess for the F parameter equal to 1. And we perform a spatially distributed calibration of the other 3 parameters by using rainfall as a benchmark. So basically, we calibrate these parameters on the basis of the capability of the algorithms in reproducing rainfall, not irrigation. In order to do this, we have to mask out potential irrigation days. So what we do is that we run this step by masking out days with no rainfall during the irrigation season, which are potentially irrigated days. And we obtain a spatial distribution of A, B, and Z. Then over selected sites where we have also the irrigation information, as for instance, pilot irrigation districts, we perform a specially aggregated calibration of F. And in this case, we use as a benchmark the total amount of water. So we test the capability of the model in reproducing the total amount of water, so rainfall plus irrigation. And we obtain a calibrated value of F that we compare with our first guess. And in case of disagreement, we adopt the calibrated value of F, and we update again the first step in the second iteration. So basically, we update the first 3 parameters with the calibrated F value. So coming to the results, we have produced with this method irrigation water use datasets within Irrigation Plus over 3 main basins worldwide. First 2 are European sites. They are the Ebro Basin in Spain and the Po Valley in northern Italy. In this case, we have products at 1 kilometer spatial resolution because they rely on Sentinel-1 soil moisture from RT1, which is produced at this resolution. And the period is from 2016 to 2020, but then actually in another ESA project for the MED, we extended in time these products until the end of 2021. And we have also changed in the new version, so in the version 1.1 rather than 1.0, we added potential evaporation from GLIM at 1 kilometer instead of the coarse resolution data, because the new GLIM version was produced, of course, in the same project in which we updated the irrigation estimates. However, the validation results that we will see today refer to the first version, so to the Irrigation Plus version. These datasets are freely available. They are in Zenodo because actually, as we will see in the following, one of the main challenges is the validation and it's the collection of in situ data of irrigation, which is very tricky. So we hope that by having freely available data from satellite, scientists that have some in situ data can perform on their own some validation and give us feedbacks on the reliability of the products. We have also a third product developed in Irrigation Plus, which is an irrigation water use dataset at 6 kilometers in this case, because it relies on Cygnus soil moisture produced by Spire. The temporal coverage is from April 2017 to July 2020, and actually the resolution is 6 kilometers, and the same applies for this product, so it's in the same Zenodo repository. we have also a paper for the method. So coming to the validation, for the Ebro Basin, we were able to collect benchmark information on irrigation amounts over 4 pilot districts within the basin, which are Algeri Baraguer, the Catalan Aragonese district that was divided into northern and southern portions, and Urgell. And in this slide, and with the same meaning in the following ones, in light gray, it's indicated the benchmark irrigation amounts, so the reference, while the black line indicates our estimates. There are some scores on top of each panel. Of course, each panel refers to a district. But in general, here we obtain pretty good results with a median root mean square error across the districts, which is less than 1 millimeter per day, a good correlation, and also a pretty low bias. Then coming to the Po Basin, here the validation is trickier because we were able to collect in situ reference data just over these 2 pilot small districts, which we are around here, the Faenza city. The districts are called San Silvestre and Formelino. And here we have basically 2 challenges. First one is that we have just a couple of benchmark sites, and also the size, it's, let's say, a bit at the edge for the 1 kilometer resolution. So we are, it's still okay, 1 kilometer, but probably we are actually at the very edge. And in fact, here what happens if you check the validation is that here we obtain lower performances with respect, for instance, of the Ebro Basin. Especially, we tend to overestimate a bit irrigation with respect to the benchmark. Then again, we have another basin with semi-arid conditions, which is the Murray-Darling Basin in Australia. Here, we were able to collect benchmark information on irrigation over 5 pilot districts, which are the Murray-Malwala, Western Murray, Marrambigi, Murray-Wakul, and Colombelli. Again, each district is the result of each district are indicated in a dedicated panel, and also colors help to understand which one. And in 3 out of the 5 districts, we obtain very good results. Then there are a couple of districts where we have some issues. Sometimes it is pretty clear why, as for instance in the green one, which is Western Murray, you can see from the zoom that is the extent is very limited, and considering that here we have 6 kilometer resolution, probably it's a matter of resolution and we underestimate. And then, for instance, there is the red one, in which we tend to overestimate, and actually it's difficult to understand really why. However, in general, over this basin, results are good. We have a median root mean square error of 10.5 millimeters per month, still a pretty good correlation, and also a low bias. Here we have aggregated results at the monthly scale because it was the resolution at which the benchmark data was available. So, possible known issues of our data sets. First one is its false irrigation estimates over non-irrigated areas, because we run our estimates over all agricultural areas, which are derived, of course, from land cover information, and these areas could be either rain-fed or irrigated, no, are mixed. Over the Ebro Basin, we more or less know actually where irrigation occurs, because it's a very data-rich basin for this kind of application. And also, the irrigated areas are pretty static in time. So we have this information, so we try to estimate how much irrigation we wrongly estimate outside of this domain. And by averaging in time during the full period of the data set, so from 2016 to 2020, and then averaging in space over the full area, we have an error that is lower than 1 millimeter per day, but it's a kind of assessment, it's a quantification. But this is possible here because here more or less we know where irrigation occurs. But usually we don't have this information. So it's also difficult for other areas to do this kind of assessment. Another possible issue is irrigation estimates during non-irrigated periods. So false irrigation alarms in time and not in space. And as an exercise here, we plotted the mean irrigation amounts over the pilot irrigated districts for each pilot area. And in light green, there is indicated the highest intensity irrigation season. So when we expect a peak, and actually for all the data set, we have a peak when expected during the main irrigation season. But you can see how, for instance, in the Po Valley, there is also another peak in October, which is likely due to false irrigation alarms that in our algorithm has produced when we are not able to properly estimate the rainfall contribution. No? So there is water from rainfall that is wrongly attributed to irrigation. But even in this case, as usual, I would say with irrigation is tricky because it is also true that over that area, there are some fruit trees that are still irrigated also up to October. So probably this could be also a track of that signal. We are not 100% sure. Then actually what we did over Europe and over the Mediterranean area with Irrigation Plus was focused on over the Ebro and the Po basin, so Spain and Italy. In the 4D Med project, another ESA project, we extended in time our estimates over these two basins, and we also extended to other anthropized basins over the Mediterranean, so over the Megerda in Tunisia and the Yero in France. But again, here we don't have benchmark information on irrigation, so we are basically trying to collect them to validate, but we have products also over these domains. Another, let's say, parallel activity, we try to answer the question if operational irrigation monitoring systems are feasible, and we did an exercise in this sense with the operational products from Copernicus and ERA5 land meteorological data. And we produced an operational system actually for estimating irrigation with the same methodology. And we applied as a proof of concept in Ukraine in the area that was fed by the dam that collapsed because of the conflict with Russia. And actually we see some nice features that discloses some sociopolitical dynamics. As for instance, if you look at the violin plots in the bottom, you can see how 2023 was the year with the lowest irrigation amounts estimated for obvious reasons. But it's not nice, this fact, of course, but it's nice that there is a correspondence with the real world somehow of what we estimate from satellite. So in summary, key messages are that up to now, monitoring irrigation water use from space is feasible. The validation we have carried out so far is focused over 3 basins, and we obtain much better performances over semi-arid areas rather than humid contexts. But it's also true that the validation here is affected by the inhomogeneity of in-situ data viability, because validation of the Po basin was pretty limited by the data viability. Irrigation retrievals could also benefit of integration with detection techniques. So it will be nice, and for sure it's the next step of this research to couple irrigation retrievals from satellite with techniques for mapping irrigation. So information coming from satellite. And also I remark that the produced datasets are freely available for fostering faster validation from the community. So final slide as required by ESA about Outlook recommendation. Of course, the room for improvement in this kind of activities is still wide. There are 2 main issues to me to be addressed. First one is that in this kind of application is essential to have spatial and temporal mismatch. It's important to have a matching between spatial and temporal resolution of data sets that we used and how irrigation is practiced and irrigation dynamics. So for instance, in this case, future missions could help. And also the main driver of this research, but also the main limitation, as you may have understood by the presentation, is the lack of in situ data. So the support from research projects that also look at fostering the building of super sites where irrigation is scientifically and systematically monitored could surely help. So that was my last slide, and thank you for the attention.
Are there any questions? Yeah.
Hello. Just a question by curiosity. Sorry if I missed something, but how did you deal to acquire the data for the in situ data for irrigation?
The in situ data?
Yeah.
For instance, it depends on the area. Ebro Basin is available because they actually have a very data-rich area. So they have data about the water flowing through the irrigation canals that feed the irrigation districts. So you can easily derive irrigation amounts delivered there. You have to assume losses, but you have the data. Then other data sets were collected within the project. So it was actually a project task. And for the Po Basin, data was provided by stakeholders and also for Australia. Yes, please. It's one component, or to better say, to me, the main issue is still a resolution, the spatial temporal resolution with respect to irrigation. Of course, if it depends also, we are using ERA5 LAN here in this kind of application, and we know that it can perform in different ways in different areas. Of course, if we do an error in estimating rainfall, this is reflected in an error in estimating irrigation, because for instance, if we underestimate rainfall, we likely overestimate irrigation. But probably here the heaviest component is the spatial and temporal resolution thing.
Okay, so I think I'm going to ask for other questions to come to the speaker at the end for the sake of time. Thank you so much. And the next presenter, we have Amir Hossain Arhari. I'm sorry if I didn't say that correctly.
I should. The PDF or
whatever you prefer.
Okay. Hello everyone, my name is Amir Hossain Arhari. I'm a PhD student from University of Oulu, Finland. I'm gonna present my paper entitled Lake Desiccation Monitoring in Persian Plateau with Causes and Effects. So, over the last 4 decades, most of the lakes in Persian Plateau are in drying process, and also some of them, such as Lake Urumia, well explained in the existing literatures. But the other lakes, such as Bakhtagan, Maharlu, and also the other existing lakes in the Persian Plateau missed a little in the existing literature, and we tried to show the drying process of Iranian lakes in this paper using remote sensing data and machine learning algorithm to answer some questions about why the drying process is happened. Although some of the factors are missed in this study because we had lots of gaps in the availability of the in situ data and data from organization in my country. But we tried to answer why the drying process happened, which factors are important, and drying process started since when, and what is the consequence of the drying. So sorry. Yes. We selected 6 basins in Persian Plateau from the northwest of Iran to the southeast of country, and you can see each basin covers different provinces. And also in the next slide, you can see the flow chart, the process we have done in this paper. First, we get area estimation. We did area estimation for the lakes, and then based on the literatures, we picked some of the important factors that can affect on the lake conditions, such as climatic factors, precipitation and temperature, cropland, drought severity. But about the cropland, we only selected the crop area, crop type, and some of the other important factor because of the unavailability of the data has missed in this literature and caused we couldn't go through deep more about the causes in this study. And also the severity of droughts also assessed, and also the discharge changes. And finally, we assessed the relationship between the lake area estimation and dust events in each basin separately. And all of the process is done using the machine learning methods, the variety of machine learning methods such as downscaling, time series analysis, regression, clustering, and prediction has been used. But in the results, I will show you which method used in which part of this study. So the first result is about the lake area monitoring. As you can see, 8 lakes selected here, and the process, the water area estimated from the 1984 to 2023 using normalized difference water index, the combination of near infrared and green band based on McPhetter equations. And also we showed the fluctuations of the lakes with 16 days, and also the annual format for each lake separately with the breakpoint detection based on the Petit test. Using the Mann-Kendall analysis, we realized that all of the trends are significant with 95% confidence. And as you can see that in the most of the lakes from the late of 1990s and early of 2000s, the process of drawing is started, and the rate of changes in the lakes varies from 50% to 100%. 50% in such lakes, in some lakes such as Urmia, and 100% in some lakes such as Hamun, Canville, Sin, and also the average of lake area computed after and before each breakpoint. So the next, we want to go through the climate impacts. First, we got the precipitation and temperature data for each basin in the Google Earth Engine platform, and we couldn't find a significant trend for the precipitation as blue line you can see here. But regarding to the temperature, there is a clear increasing trend which is significant with 95% confidence, and we've found that around 1 degree Celsius temperature increase since 1970 to 2020 based on ERA 5 data. And the breakpoint is very close to the breakpoint of the lake area we estimated. It's also started since the late of 1990s and the early of 2000s in all of the basins. And next, see that how much drought has impact on the lakes. We got the Palmer Drought Index with annual format in these years. And as you can see, after the breakpoints, the number of negative values for PDSI highly increased. That means that drought condition also increased, but we can't see a significant trend in the precipitation. To go more deep about the drought condition, we used a standardized precipitation and evaporation index with 12-month format for long time series analysis since 1980s to 2020. And here you can see that after the late of 1990s, the number of the dry spells, lengths, depths, and frequency of the dry spells highly increased. And also we did a clustering based on the duration of each dry spells, the lengths of them, the maximum and the minimum value, and other statistical criteria. And we found that the number of multiple droughts, multiple severe and extreme drought happened in the most of the lakes in Iran. And also we think that maybe that is one of the main important criteria that caused the lake reduction, water reduction in the basins. And also the next, we did cropland area monitoring for each basin, but because of the lots of gap in Landsat scene, we had to use downscale procedure for the NOAA data, because we decided to use NOAA NDVI products because it is daily format available since 1984. And then, but the main limitation in this data is about the spatial resolution. It was about 5 kilometers, and we used linear regression modeling and combination of NOVA and MODIS and DVI product. It should be 500 meters, not 1 kilometer. And we did downscaling for all NOVA products. As you can see, the NDVI in 5 kilometer and 1 kilometer helped us to see the croplands much better than before. And then we used this data to monitor cropland area alongside the lake area variations. And as you can see here, again, after alongside the lake decreasing, we can see an increasing trend in the most of croplands area, in the most of the basins. But in some of the basins, such as Hirmand and Jazmurian, the the agricultural activity is not very important. Here we have lots of other problems, such as transponder issues and something like that, that caused the water reduction over the last years. But the important thing is that the crop increasing extent ranges from 47% in Urumia to more than 100% in Mahalu and Bakhtagan basin. But in some of the basins, we can see that over the last years, the number of croplands area or the percent of cropland area reduced because of the unavailability of enough water and also the drought condition. So, but compared to the before 1990s, in all of the basins except Hirmand, we can see the increasing trend in the cropland activity. In the next part, we check the discharge impacts, and also you can see the same trend is visible between the discharge and lake area. Alongside the lake area decreasing, the discharge also decreasing, and also we found that around more than 80% on average, the discharge values reduced in each basin. But because of the unavailability of enough discharge station in this study, we couldn't do more deep analysis regarding to the discharge impacts. And also you can see that the same trend, there is a similar trend between discharge and lake area, and the decreasing trend in the discharge just started before the lake area decreasing trend. 1 year or a few years earlier, we can see that the process of decreasing started. And then using regression analysis, we tried to find the important factor for each criteria. but it is not completed, and also it is not very accurate because lots of other variables missed here, such as political situations, transboundary issues, and also crop type, irrigation, groundwater, and lots of things missed here, but this is still in progress, and also we want to do update it in the next step. But we found that among the selected parameters, such as drought and air temperature, they are, for example, drought and air temperature had more importance in this study compared to the other criteria selected. And we found that cropland area is not very important. Maybe crop type and crop consumption, water consumption by crop could be more relevant and more important from a statistical point of view. And finally, in the next slide, we saw that there is an inverse relationship between lake desiccation process and dust and also dust particle thickness. As you can see, over the last 4 decades, over each lake, alongside the lake area decreasing, the thickness of particles also increasing. And the breakpoint shows that since the late of 1990s and the early of 2000, the thickness of the particles also increased. And here we computed the frequency of dust events over each basins, and you can see the hottest spots over each lakes. That shows the higher frequency of the dust situation in this area, because now we have exposed beds that causes to increase the number of dust frequency in these regions. And then in the final steps, we plot the relationship between the lake area and PM2.5, although there is not a strong relationship here, but you can see that most of the high PM2.5 values occurred in the lowest area. As you can see that, it shows that in future, this relationship can be stronger. And also this is an alarm for the air pollution and also air quality in the regions nearby to the lakes, urban areas, and also the environmental condition. That's it. Thank you for your attention.
Thank you. Any questions? Yes.
You mean about the downscaling process? Why we didn't use what method? Which method? Oh, yeah. The problem was that we wanted to monitor crop area since 1980s to 2020, and also because of the unavailability of satellite data before 2001, such as MODIS, we had to do some sort of downscaling process. And first, we make a linear relationship between MODIS and NOVA since 2000 to 2020. And then based on the estimated equation, we forecast the NOVA 1 kilometer for the before 2000, actually. Yes. Yes, we did although this is 500 meter, because the MODIS NDVI product is 500 meter spatial resolution. And about the uncertainty, we compared the area estimated by the NOVA 1 kilometer with some of the reports that is available from Iranian Agricultural Organization. and also we good a correlation for the 40 years in the scale of whole of Iran around 70% correlation actually. Okay.
Yes, yes.
Yeah. The method we used for the quantification was ordinary least square regression. Actually, we used this method. And also we selected here lake area considered as a dependent variable in the equation, and some other factors such as cropland area, such as drought condition or the drought value, and air temperature and precipitation. These are considered as independent criteria, and then we combine them in the model, and we based on p-value less than based on the p-value and r-square, we realized that the importance of each feature could be in this range actually. Yes, yes. Yeah.
Or maybe it's a naive question, but why does events be attributed to line? What's the history?
Between what?
Between the attribution of these events to
actually, these are not events. Based on the recent literatures, for example, based on the recent literatures, we realized that the main criteria that always explained about the lake condition are climate, cropland, drought severity, and discharge changes. For example, in Iran, we know that, for example, about 80% of water consumption is because of the agricultural activities. Based on our information and also information available in the papers, we selected these criteria. For example, about the climate condition, we thought that maybe drought condition and less precipitation caused less inflow to the lakes, and also that's one of the consumption. And also sometimes in some literatures, dam construction considered as one main option that reduce the amount of water coming to the lakes. And also these are based on information that we have in this area that could have impact on the lake condition. We didn't explain about the physical relationship between these phenomena actually.
More questions? No? Okay. So thank you. So.
Now it's time for Sofia Armida, sorry.
Okay, so good afternoon, everyone, again. I'm here presenting on behalf of Isabel Trigo, who's unfortunately couldn't be here. And I'm going to talk a bit about the Landsat. So I work for the Landsat, as I said before, and show you some examples of how we can use satellite-derived variables in the context of land process studies. Okay, so at the Landsat, we are responsible for the operational generation of satellite products based on EUMETSAT satellites. So we have the Meteosat second generation series, which is a geostationary satellite, and then we have the METOP series, and obviously the upcoming new generation of satellites that will replace this current series. And we generate variables that are related to land surface processes. So we go from radiation, energy balance, and vegetation conditions. Okay. So a few examples of the variables we produce that are relevant specifically here in the context of hydrology. So we do derive a surface albedo, for which we use all available observations throughout the day to compute the BRDF. And from the albedo, we can derive a set of vegetation-related variables that are well known, like the fraction of active synthetic, fraction of available photosynthetic radiation, and the leaf area index. Then we also have products for land surface temperature. We have currently have a product that is we call a level 2, which is based directly from infrared observations. And then we have a kind of level 3 product where we combine the infrared observations with estimates from an energy balance model to fill the gaps of clouds. So we get an all sky LST with a high frequency of observation. We also have some evapotranspiration related products. So we have the reference evapotranspiration, which is sort of a evaporative demand of the atmosphere, so to speak. So the evapotranspiration just variation just associated to the atmospheric conditions for a perfect green surface, as we have here. And then we have the actual evapotranspiration, which is estimated using a surface energy balance model, very similar to the one used at the CMWF, but in this case, the model is constrained to the maximum, to all the satellite observations that we have to a maximum extent. So we use albedo, leaf area index, radiation, soil moisture, all coming from satellite observations. Here is just to tell you that all the products that we produce are very carefully validated. This is just an example for land surface temperature, and we also provide estimates for most products. We provide estimates of uncertainty, and we also are currently trying to implement strategies to validate those uncertainties as well. So now here I have an example of how we can use this type of variables in the context of studying processes related to the water cycle. So here you can see the full time series of the MSG, and we have anomalies for the Iberian Peninsula, anomalies of land surface temperature, and anomalies of vegetation cover. And you can see here very well the three major droughts that we had in the last few years. You can see really strong anomalies of vegetation. And naturally, if you look into the anomalies of temperature, usually these are associated to very warm conditions. Usually when you have a drought, also have heat wave events. So these are very, as you can expect, very correlated. And also another variable that obviously is very correlated, it's the fire radiative power. So here you have anomalies of fire radiative power. You can see that the seasons where you have very dry vegetation, which is very much more flammable, and then you have very warm conditions. Typically, we have also seasons that have very large events of fires. These are the cases for all these 3 years. Now, another way to look at this is also when we look, especially and also in terms of time, how these variables correlate. And it's interesting to notice, for instance, here we have correlation maps between the surface temperature amplitude. So this is the amplitude of the diurnal cycle. Because we have the full diurnal cycle of LST, it's very useful to compute the amplitude. And you can see here that in spring, in the northern parts of Europe, there's actually areas where you get positive correlations. So having warmer temperatures usually means that we probably have more radiation available. And because there is no water deficit, it correlates into a vegetation growth. So you have positive correlations. But as you go to the summer, this correlation is lost because probably the soil is more dry. You don't have enough moisture to keep the vegetation green. So it starts to decrease. And the exceptions are usually high altitudes for obvious reasons, and also very, very high latitudes where you probably still have enough water and the temperature are usually much cooler. So having warmer temperatures would benefit the vegetation growth. So related to this that I was discussing, we need to consider the underlying feedback mechanisms. And so when we have wet conditions, we have evaporation and plant respiration, and they are not limited by the amount of water. So the main limitation in terms of evapotranspiration will be the amount of energy that is available. So if there is more solar radiation, so usually warmer temperatures, there will be more energy available for the plant to evapotranspirate. And at the same time, that evapotranspiration will act like a cooling, evaporative cooling of the temperature. So there's a sort of a feedback where you have bit warmer temperatures, but then they are sort of regulated by the evapotranspiration. And so you basically in an energy limited conditions. Then when you don't have enough water, what happens is the plants have to control the water loss, so they stop evapotranspiration. This decreases the evaporative cooling, so increases the temperature, which further contributes to the stress of the plant. So here you have a sort of a positive feedback where increasing the temperature leads to even more stressed vegetation that's because cannot evaporate will even increase more the temperature. And so we call this a water limited state. And so how can we study this when we want, so if we don't want to use, because you probably know that there are a lot of methods that to compute evapotranspiration, a lot of models available, but they are not exactly derived directly from remote sensing. So there are a lot of uncertainties associated to that. So how can we go around this or even use the data that we have available from satellites to confirm that our evapotranspiration model is performing correctly? So this is an interesting study that was done where we have here it's for a site. So this is with the satellite data. So it's severely, you have here the LST daily amplitude, and then you have SMAP soil moisture. And it is a few days after a rainfall event. So basically you could think of the time going from here when you have high soil moisture because it just rained, going this way. And what we see is that while we still have quite a lot of soil moisture, the temperature amplitude stays very stable. So we are in that energy-driven state where the plant has a lot of water to do all the photosynthesis, evapotranspirates without much limitation, and so it keeps the temperature cool. And then as we go to these sort of critical points, the amplitude of the temperature starts to increase very rapidly. So here we go from the energy-driven state to the water-driven state, where having less water, the plant cannot always do evapotranspiration, which in turns does not cool the temperature. So temperature increases and you get very high. And this is something that we can use to check if, when we are trying to model evapotranspiration, if this transition between water limited to water limited regime is being well captured. And here is just to show you another more recent example. So here we have vegetation cover anomalies for summer of the last year over Europe. You can see there are strong anomalies, negative anomalies here in France, a bit in the British Islands, here in this area very marked. And it's not very obvious from the mean, the anomaly in the mean temperature, what would be. So there's overall warmer temperatures than normal, but that's very recurrent nowadays. But actually, if we look into the anomaly in the maximum temperature of the day gives us, again, information of the amplitude of the temperature. You can see very clearly where these regions where we have, so we have a deficit in the vegetation, and we also have very much warmer temperatures than we would normally have. So this is that state that I was mentioning before. And actually, when we look at our evapotranspiration product, you can see very well, in this case, the anomaly in evapotranspiration. And you can see also very well when you compare the actual evapotranspiration with the reference evapotranspiration, so the evaporative demand of the atmosphere, you get a very strong anomaly in this region and also here in this region. Here, the anomaly in evapotranspiration is not that obvious, but then when you compare to the reference, you can see it a bit better. And this is just for reference what the normal looks like. And here, just a closer look, so you can see it's just an area over France, and then you can see, I'm sorry, I can see very well. You can see that here so this year is pretty much warmer than all the others almost all year. And you can see that actually up until around May, that actually benefits vegetation growth. So over here, you actually have more vegetation than the normal. But then there's a sort of breaking point that I mentioned where you continue to have very high temperatures, but the vegetation starts to decay because the amount of water cannot sustain anymore the vegetation growth. And then you get even warmer temperatures. Here in this case, this is for the British Isles. So the temperature, it's actually not that warmer here, and there's a sort of a increase in vegetation. And you can see here where suddenly you have a very warm month, and it causes the vegetation to drop. So now the same area over France, but looking into the evapotranspiration, doesn't seem to be nothing. I mean, you couldn't, thinking about this anomaly in vegetation, you wouldn't think much of it because actually the evapotranspiration is still quite high, even having such strong anomaly. But then when you look into the reference to evapotranspiration, so this would be the evapotranspiration demand from the atmosphere, you can see that it's much higher, much higher than the normal. And so what happens is that although there are probably conditions for the plant to have evapotranspiration, the conditions of the atmosphere are so extreme that it causes the vegetation to go into stress. And so when you just plot the ratio between the two, you can see very well this drop associated to the decay in vegetation cover. Okay, so this is just a few final remarks. So the signatures of drought and heat waves can be well captured by satellite products, and you can use several level 2, level 3, soil moisture, vegetation, land surface temperature, or even higher level like evapotranspiration, although there's, as I told you, modeling involved, so be aware that any certainties are going to be higher. Looking, as I discussed here, looking into the diurnal cycle is very useful because it's very linked to the soil moisture and vegetation atmosphere interactions. So this is having this diurnal cycle of LST can be very useful. Also, when we consider satellite estimation of evapotranspiration, they are not derived directly from satellite observations, as I said, but they can still be a useful tool to monitor the water loss and the plant stress together, and especially together with the atmosphere water demand. It can be very useful tool to study, monitor drought affected areas. So all the data from Landsat is available in real time, freely. It covers approximately 20 years and will be continued for the next generation of products. And with that, I finish my presentation. Thank you.
Thank you. Any questions?
Yes. Snow? In these cases, examples that I gave, I didn't use snow. We do use, obviously, we use snow when computing the LST because it changes emissivity, but that's pretty much what we use. The snow product, it's actually derived by the HSAF. So although it is kind of a land variable, we are not responsible for the production of the snow cover. Yeah. So here I was more focused on Landsat products, but yeah, obviously snow it's relevant as well. Okay, so our next speaker will be Cynthia.
So good afternoon, everyone. My name's Cynthia, and I'm going to present this work named Compound Stream Sea Level Events in an estuarine environment combining in situ data, satellite data, and modeling tools. So this is the list of contents that I'm going to follow. First, an overview of the project in which this work is inserted. Then an introduction and objectives of the work. Then I will explain the study area, then the methodology, including the numerical modeling model setup and the satellite-derived bathymetry. Then results and discussion, conclusions, next steps, and outlook on recommendations. So this work has been developed under the project EO@Sea that is funded by ESA-EO4 Society. This project joins numerical model experts and Earth observation experts to analyze the latest advances in Earth observation technology to provide a reconstruction of extreme sea level events in different test regions, improve the understanding of understanding and predictive capacity of extreme sea level events and its related hazards, and also assess the potential of the project's outputs to prepare for this, for the impacts of this type of event. So I will move now to the introduction of objectives. So first of all, why is important to focus on the study of estuaries and transition areas. So these areas act as coastal protection to sea level rise. They are also a shelter for industry and other activities like port or recreational sailing, also occupation. They also act as a source of biodiversity with a lot of large amount of different vegetation that can act as carbon sinks and also as a food source. So these areas are not only linked with continental processes like river discharge and rainfall, but also with processes that take part in the coastal area, which can be astronomical tide, storm surges, waves. And this leads to this scientific challenge, how these processes are interacting and during these extreme sea level events, and how can they affect the low-lying areas. So what is a compound event? A compound event is an extreme sea level event that results from the combination of more than one driver. Extreme sea level drivers are storm surge, astronomical tide, waves, river discharge, rainfall, and these drivers can occur isolated, but when they occur, one or more occur together, the risk is highly incremented. So the objectives of this work are to evaluate the capacity of the advanced science tool to both improve the understanding of these events and to improve the predictive capacity of them. So moving to the study area. This study area encompasses the Tagus estuary, which is located in the central region of Portugal. This area have a extreme, like very energetic dynamics, and also an important discharge from this Tagus River. The regions more impacted are low-lying areas, as Commerce Square, but it's here's a picture of a random event. And then also another part like Carcavelos Beach or Costa de Caparica that are highly influenced by extreme waves. So now I will explain the methodology we follow. Different tools and data sets were used in this study. First of all, the models. We used two models. One of them is the Moed circulation model, which is a three-dimensional water modeling system developed here in Portugal, in Maretec. And this model allows the simulation of different processes at different scales and different systems, like estuaries, open ocean. On the other hand, we used the SWAN model, which is a wave model developed by Delft, which also computes waves in coastal regions and inland waters. The in situ datasets that we used are the river discharge from different river stations located in the Tagus estuary. Then we used bathymetry data from some surveys that the Portuguese Hydrographic Institute did, and also some wave data that we use to validate the wave models that comes from a buoy located outside the Tagus estuary. And also an important talent of this work was to analyze the importance of satellite-derived bathymetry in our model domains. So we tested this satellite-derived bathymetry in our domains. So all the tools and data are integrated into a modeling approach system, which consists in a two-way coupling between the MOID and SWAN model. So first of all, we run the MOID model, MOID circulation model, and we get like water level as an output. Then we use this output as an input for the SWAN model. And we get this list of, I don't know, this is not working. Okay. This list of wave parameters, like significant wave height, main wave direction, wavelength, mean wave period, orbital velocity, and radiation stress. And we use all of these parameters to run again the MOID and to force the model waves. After running again the MOID, we get the water level, including all the processes like storm surge, tides, river discharge, waves, and currents. So our colleagues from the consortium derived this bathymetry, derived the bathymetry for the Tagus River mouth, which is an important, it's a really important location because it's highly hydrodynamic, and also there is a lot of sediment dynamic in this area, a lot of both erosion and deposition. So it affects a lot the hydrodynamics in this area. And it's really important to map it, to introduce it in our models. So yeah, they construct this bathymetry based on images of Sentinel-2 mission from 2018 using optical inversion. The rest of the, like all the validation and the methodology followed for to derive this bathymetry can be found in the poster 115. So then what we do was to use this satellite-derived bathymetry from Sentinel and merge it into our domain, our modeling domain. That is 1 kilometer resolution structure grid. And yeah, and we did the interpolation for our domain. So the MOID model setup consists on different sources of data. Open boundary conditions were extracted from a Copernicus model with a Copernicus model for the regional area of the Atlantic and Iberian area. We used salinity, temperature, water level, and also velocity of the current. The bathymetry, as I said before, we used some data from the Hydrographic Institute of Portugal and EMODNet, and also this part I explained before from Telespacio, the satellite-derived bathymetry. Then to force the tides, we use the components of FES 2014 and also the water level from Copernicus. Then the atmospheric forcing, we used air temperature, atmospheric pressure, relative humidity, and wind velocity from AROM, and also solar radiation and downward wave radiation from WRF. And the river discharge, we use data from EvoNet and MOID land model, which are time series and climatologies. To run the SWAN model, we use, as I said before, we use the water level from the MOID water model. Then we use the same bathymetry and also the same resolution as in the MOID run. And the boundary conditions, we are using those coming from Waveries, which is a global reanalysis of waves available in Copernicus. And we used significant wave height, also the period and direction. So what we did in this work is divide into run the models in normal conditions and run the models for extreme events. So in normal conditions, what we did is to validate the satellite-derived bathymetry within our circulation model system, then validate the sensitivity of SWAN model separately, and then do a two-way coupling between both circulation and waves models. This part of extreme events is still ongoing, but I will show some results, some preliminary results. So what we did in this part was to simulate an extreme event, an historic extreme event, by using the wave data from this event. Then we coupled these results from the extreme event into two different scenarios. One scenario of the circulation model by using a regular discharge of the Tagus River, and another simulation from this circulation model, but using a stream discharge that we found in the literature, because we didn't have like a data set of an extreme proper stream discharge. So I will show now some results, but it's important to note that these results are preliminary. We are still working on this. So yeah, first, yeah, here I'm showing the results of water level that we obtained by using the different bathymetries. So in orange, we have the modeled water level using the in situ bathymetry. And in green, you can see the same results, but using the satellite-derived bathymetry merged with the in situ bathymetry. We did a comparison with the Cascais Tide Gate, which is located here in Cascais. And we found out that the correlation between the Cascais in situ bathymetry, the Cascais Tide Gate and the in situ bathymetry was the same as the one using the satellite bathymetry. And we found that the root mean square error was 0.087 in the case of the in situ bathymetry, and 0.088 in the case of the satellite-derived bathymetry. We also obtained the same really similar results for the other points that we investigated. It's where Carcavelos, Costa da Caparica, and also Commerce Square. So we decided to use this satellite-derived bathymetry for the rest of the simulations. So here we did a sensitivity analysis of the wave model. We run only a period of 6 days, approximately, and we found that our model was reproducing the real conditions that were measured by the Porto de Lisboa buoy, which is located in here. And we found that the correlation between both datasets was 0.95, and the root mean square error was 0.95. 0.16, sorry. So here we try to assess the wave contribution to water level. Here we can see the orange lines showing the circulation, the results of the circulation model, and the blue show the circulation after coupling both models. Of course, like we cannot see anything, but here we have the differences between both, and we can say we can see like the influences on the waves in sea level. We can also see that they have a kind of correlation with the tides, with the amplitude of the tide. And here, like we are showing the differences between water level with a simulation using a stream discharge in red, and the same using a normal or regular discharge in blue. For the Cascais gates, the buoy, and also the Commerce Square inside the estuary. We didn't find a lot of like importance in the stream discharges for this region, so we will try to do another simulations with higher discharges. So some conclusions and next steps are that satellite-derived bathymetry does not present a high influence in the circulation results compared to the in situ bathymetry, but maybe it can have a higher impact in hydrodynamic processes in shallow waters. The modeling results appear to reproduce the real conditions. Streams river discharge reveals a slight increase in water levels. And another things that some things that we want to do now is to test the total water level product that we got from this EOHC project into like as a boundary forcing for the circulation and waves model, and also test this higher river discharge. And then some outlook and recommendations that we found during this work is that they are not digital twins engines capable to integrate in situ data, modeling data, and Earth observations in a single system. And it will be a good opportunity to have a call to integrate the three of them. And also we didn't find enough river and estuarine data for water levels to evaluate our model outputs. So maybe we can explore the potential of some sensors like SWOT, or maybe another ones. And that's all. Thank you.
Thank you, Cynthia. Any question? Yes, please.
Hello, Nuno Moreira from the Portuguese Med Service, IPMA. So very interesting work and very relevant for our story here. It's a very important place. I've seen that you tested the case into 2019, and you showed, of course, the images for Hercules. It was 2014. I was just checking. Do you plan to test this case? Are you limited by some data, perhaps model data? I was imagining, but that's a question. And then you are using AROM with 2.5. Of course, can you use a higher a lower resolution like European Center, for instance, for getting to going back more on time to find cases?
Okay, first of all, yeah, we used, let me just find, yeah, we used data from the Hercules storm, which was in January 2014, because we didn't find extreme event on other years where we have some data to validate. So we tried to do a yeah, like we wanted to generate extreme scenario, so we took real data for another scenario, and that's the reason why we cannot validate this coupling, like this synthetic coupling. So we decided to validate this the models before, like to be sure that the models were working on this domain, and then do the rest of the work. And the other question, sorry.
It was the question of the European Center, for instance, because it can go back more on time. And so AROM has 2.5 kilometers. The European Center has 9. Would 9 kilometers be enough for you, or not so good already? So the 2.5 is really the resolution to go for this.
I mean, we used to use this AROM with 2.5 kilometers of resolution when we are running MOID, and all the validations are like quite good. So I don't see any problem with using. Yeah. Yeah, that's the point. Like we have data since I don't remember exactly the year, but the thing is we also have to validate our data with the tide gate and the buoy, and we need like we don't have a lot of data like from years ago, so it's okay to use their yeah.
Okay, thank you. So, because we're a bit behind on time, I'm going to ask to other people that have questions to ask during a coffee break or something. And now we're going to the discussion part of the session. So maybe if your question is relevant for the discussion, you can. Cynthia, maybe pode pôr o slide daquele questions. Okay, so we have here a lot of questions. Sort of start the discussion. You're welcome to suggest any other subjects that you find relevant. So we have here a question on whether what are the caveats and the advantages of relying on reanalysis data sets versus satellite data sets when studying all these processes? What are the most significant gaps in satellite databases that are relevant for hydrological processes? Are there any gaps in essential climate variables? Are there, on the other hand, are there any satellite observations or products that you think they are underexplored? How important is the representation of satellite products uncertainty? what are the most significant gaps in situ? I've seen here several people mentioning in situ that are relevant for hydrological processes. I think I repeated one question, right? Okay, no problem. What is the role of data science and machine learning in the scientific advances, and how can new AI tools be leveraged to understand processes in hydrology? How can these solutions be applied to operational frameworks, and what are the steps and adaptations that would be necessary to implement them? What methodologies can effectively integrate in situ and satellite data? How to communicate alarming results to society and the public, and also considering water scarcity. How can data result from research be applied to enhance water management? Any suggestion, any comments? Is there anyone here that wants, for instance, comment whether they prefer? Yeah, sure. Data latency, no, but if you want to comment about. And what kind of latency can you give an example? I don't know, in your field, what kind of latency would you think would be interesting or? Okay. Yeah, I think here also it's important to separate what is forecasts and any institute that is responsible for advising policymakers. And then when you want to study processes, in this case, where you more focus on linking several variables, maybe in that depends on the application. Obviously, any study that we make, we want it to have an impact, so it has to somehow lead to a result that we can present to the community, as said here. So but I wonder if obviously depending on I don't think it will be feasible at any time to go from using forecasts, which are models, to make decisions, especially when we're talking about storms and things like this. If it's something that it's a slow process, like a drought, or maybe satellite can be used. NRT products in satellite usually have a very good latency. I think our at the Landsaf, it's I'm not sure, maybe half an hour, 1 hour. So it's, but I'm sure you would have to go to the agencies that are responsible for the operational production. Then you also have products that are generated in the scientific community that are produced offline by individual financing. So those don't have an NRT process, but yeah, I see your point.
Of course, I'm from operation. I'm very operational. I'm not so from research. So maybe to answer to your question, and I think there is clearly a separation between what you have as, let's say, the wave forecasting or precipitation forecasting, and you have warnings and you have early warnings. So you have the systems more or less in place. At least in Europe, we want early warning for all, right? That's for the whole world. So you have to work on this clearly. But I agree with Sophia. I think that the challenge is maybe on these kind of aspects that do not have already implemented these early warning systems. And you have, of course, the drought, which is slowly growing. So when do we get to the point and decide that, okay, this is a problem now? So I think clearly that's when scientific community can come and intervene, because there are no warnings. We have been discussing this in Meteoalarm, which is the European organization for warnings, that do we need a warning for drought? Then it would not be clearly the same branch that would be doing this. It would be another one, but we can include in the same system, of course. But it's clearly getting many agents in the same team. And I think that's a challenge. And for drought, I think it's clearly a challenge. But I know in Portugal there are meetings with the high level meetings following the drought, at least every month when there's a problem, even every 15 days. So of course there is a place there for the government to know. But I think clearly that's an issue for these topics that are outside what we already covered. I think it's clearly an issue.
Any other comments? I think was also mentioned here in the presentation, the limitations in access to in situ data to validate. Would you like to add something more? I think this is mostly universal in all areas. In all areas of remote sensing, we always want more data to validate. Yeah.
Whenever we see a presentation, great job. Based on your data deploy model, sensor-based model, stick to small time side note. Stop giving those things into data. Or makes sense to do it. Say that it's better to have some connection. With that person that say
Any more comments? Anyone want to comment on maybe gaps in satellite data or satellite data that you think are underexplored? terms of hydrological processes. Does anyone have any comments on machine learning, AI tools, maybe? Mhm. So it's that it's underexplored, you think? Okay. Mm-hmm. I'm sure this is a topic in many sessions. Mhm. 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 Yes, I think definitely. Sometimes people think about machine learning as a sort of a miracle solution to everything, and it's just a more complex linear regression. So any data, it's very reliant on the data that you train it with. So if you don't have enough data, enough information to correctly train it, it's not going to give you a good answer. I had a very good teacher of statistics and statistical methods that had a very interesting approach that said you can have the best model in the world. If your training data is trash, then your output is trash. It doesn't matter how good your model is. So I guess that was already valid before all this machine learning sort of boom. But yeah, it's valid for any model, statistical model. So it's important to have good quality data to train your machine learning. Mm-hmm. Mm-hmm.
Try to ask things like what was the training period or which percentage big portion of the community or just backwards.
Mm-hmm.
Small group that big this stuff there is the application.
Mm-hmm.
So you get a lot of responsible.
It's very dangerous. Yeah, I think the lack of reviewers, it's general and not just in that area. So, yes, yes. And it's very dangerous territory because I think things need to be done very carefully to have confidence in the.
People talk about them, but don't mention about the costs.
Mhm.
So maybe one plants will be out. And food itself, you cannot tell a person sitting on the shoreline and want to make a decision and say that just wait for 1 week and give me the answer for the next 3 hours.
Yeah. Actually, the developments in machine learning for meteorology have been very good and done very well. So the scores are very good. It's really fast. So up until now.
It's a huge gap for science. I still see people talk about ESA-ESRIN 10 years ago. They have a really advanced everything. They know the problem. Now we still use that because there are available libraries. It's not one line of code. It's really hard for making understand real edge of the science and something. So I have respect. It's good to have for that.
It's the best way to test it, right? It's just open it to the community. And they made a huge investment in computer science people because they understand the importance. The problem is that this is a very competitive area, and in science is usually very hard to pay a person that it's really good in computer science, because especially if it's public financing, I feel like it's really difficult to hire someone in this area, because they can, in the private sector, they make, it's machine learning is everywhere now, so it's a struggle. Exactly, yeah.
So all of you are they call it the speaker. My point is that he published a paper. You want to publish in your you'll report with that. What publish science is wrong. More publishing reading archive. And we still see papers. They already told something. My point is, it's better to take a look at the and most doctors in the libraries
Okay. I was not checking the time, but I think we were 10 minutes behind, so we are already finished our 20-minute time for the discussion. If there's no more comments, I think I'm gonna close the session. Thank you all for coming and see you tomorrow.